disable enable room.
Yeah.
Let the students come in.
I think our speaker has not yet joined.
It's Swati, right? Swati is the first.
Dr. Nandi, I just made you co-host. Okay.
Okay.
Yes.
Yeah, it's fine. The live is working.
We are live now, right?
The YouTube.
Yes.
So some of the participants, they are telling they can't join the meeting.
Why is that?
Is there any
They should be able to join, right?
They should be able to join. There is absolutely no bar.
So is it from
1 minute, 1 minute,
Doctor?
1 minute.
We already have
Unlocked. Oh, okay. Okay. So there was some unlock with them. I think we have.
They can try again, maybe.
I can try.
Yeah, now they are joining.
Okay, I think there was some child. I think maybe Swati
Yeah,
also.
yeah. Yeah, I think, yeah, because it's almost time. So for some reason, I think people were on. Yeah, so Dr. Swati has joined us.
Yeah, Dr. Swati already joined.
Hello,
Hello.
Swati.
Yes, Dr. Swati.
Hi. Hi.
Good afternoon.
How are you? Good afternoon. I have been trying to join for the last 10 minutes.
I'm sorry.
Okay, yeah.
That's why they are
Sorry, yeah.
very less participant.
No, there was a technical issue, so something got solved. Yeah.
I see. Okay.
It's time now, so Dr. Swati, we should be. Can we wait for another few minutes? So because
Yeah, I
other
think we should
participants
wait
are
for
also
5
unable to
minutes.
join because of.
Yes.
Yeah, we'll just wait for a couple of minutes.
Yes.
Good afternoon, Swati. This is
Hi,
Rajesh.
Rajesh. How are you?
I'm doing well. Sorry, I because of it was my mistake or something. I pressed here. I think there was some. This one had locked out everybody else in the meeting.
Yes.
I was also wondering why there was only few members are not joining.
I see. Okay. I was thinking there was some error from my side.
No. Anyway, thanks for joining.
Sure.
Hello. Let me just mute everybody else, so otherwise.
So is the college open now? Or
No,
no?
we
Okay,
are taking the classes in online.
online. Do you
Yeah.
have residential facilities, or all the students are there?
No, there are some facility. There is a hostel for the girls hostel for the
Okay.
students.
But right now they are not staying on campus.
In any case, we are a new university, so things are all still coming up. So we
I
are
see.
still trying to find a footing, and then we face this all of a sudden.
Where are you located? I couldn't get the coordinates properly.
So this is about say 35 kilometers south of Calcutta.
Oh, I see.
From the heart of Calcutta, it's about say 35 kilometers further south.
Okay.
So it's close to the Ganges, down south.
Okay.
Pretty much a coastal area.
Mm-hmm.
Yeah, we would like to have you here sometime in the future, if possible, in the university.
Sure.
I mean, yes.
Sure. That would be. So how many girl students are there overall?
So this is a women's university. So
Yeah.
of course, all our students are girls, and I think
1,000.
we have
1,000.
yeah, 1,000. No,
For different academic.
yeah.
Okay.
I think
Okay.
it's 1,200 or 1,300 now.
Yeah.
Dr. Nandi.
Okay.
Yeah,
Okay.
Okay.
yeah.
More than
And
1,000.
we have about 46 in our department.
Okay.
PG1 and PG2. So
Mm-hmm.
it's only a PG university. We don't have an undergraduate program here.
Okay. And how many faculty members in chemistry? Let's say.
There's just 3 of us now. For now.
Gosh. Okay.
Yeah. So yeah, it's a bit of a workload for us. So
Hmm.
we will be getting new faculties, of course, in the future. I thought I muted everybody.
But we are taking the help from other resource person from the different institute
Nearby
also.
places.
Yeah. So IIT Kharagpur, Jadavpur University, and different places.
Okay. Okay.
Raj, I think we need to start. I think.
Yeah, I think, yeah.
I will.
So we have
Yes,
now
I think we
30
need to
participants
start.
that they are joining. So we can start since 1:05.
Yes, I think
So-
we're good to start now. Yeah.
Okay.
Okay, Mr. Rajesh, I just clicked on that option like mute participants upon entry, but I don't think everybody is getting muted. Yeah, for now everybody else is muted. I can see.
Okay. So I'm
Yeah,
going to
we should
start.
be
Okay.
we should be fine. Yeah.
So
Yeah.
very good afternoon, all the participants and the speakers. So we have with us today Mr. Rajesh Parishad from RSC Chemistry, who will deliver a lecture on the valedictory session. So in the first lecture, we have with us Professor Dr. R.S. Swati from ISAT Trivandrum. He will deliver a lecture on the physical chemistry. Then we will have the Dr. Guem Bhinsai from University Paris Saclay and Dr. Debabrata Maiti from IIT Bombay. So for this technical session for the physical chemistry, I would like to Dr. Pujarini to chair this session.
So thank you. Good morning to all. Rather, it's past afternoon. So good afternoon to all, and thank you, Dr. Nandi. So I think we can just proceed with this session without further delay. And I'm happy to introduce to you the first of our speakers this morning. That is Dr. Swati. And before I request her to begin her lecture, let me just give you a brief introduction of Dr. Swati. So Dr. Swati did her integrated BSc course at the Regional Institute of Education, Karnataka. Then she obtained her MSc degree from the IIT Guwahati, and she obtained her PhD at the Indian Institute of Science, Bangalore, under the supervision of Professor E.L. Sebastian. And since September 2010, she has been a faculty member at the Indian Institute of Science, Education and Research, Thiruvananthapuram. So Dr. Swati had several awards and recognitions to her credit. Just to mention a few of them, she is the editorial advisory board member of the journal called ACS Applied Materials and Interfaces. And she has been the recipient of the Platinum Jubilee Young Scientist Award of the National Academy of Sciences, Allahabad. She has received the Women Excellence Award from the Department of Science and Technology, Government of India. And she has received the Young Scientist Award from the Indian National Science Academy, New Delhi as well. And she was the recipient of the Distinguished Lectureship Award of the Japanese Chemical Society for her work on theoretical chemistry. And she has been also an associate of the Indian Academy of Sciences during the duration 2014 to 2017. She has participated at the 59th meeting of the Nobel laureates in Landau, Germany, as a representative of the Siemens Information Systems Limited, and so on. And Dr. Swati is a distinguished scientist in the field of theoretical chemistry, and she has several very good publications to her credit, 35 of them, about 35 of them in total. And she's also active in teaching, so she is a regular teacher for various physical chemistry courses at either Thiruvananthapuram. So with this very short introduction, let me request Dr. Swati to please begin her lecture, and we would cordially once again like to thank her for making time out for our webinar and being with us, joining us this afternoon for this webinar. Thank you, Dr. Swati. You may please proceed with the lecture.
Thank you, Dr. Pujarini. Can you hear me?
Yeah, you're absolutely audible, ma'am.
Yeah, thank you for those kind words. And let me first begin by thanking Rajesh and Dr. Nandi for having extended a kind invitation to be delivering this talk. I'm very happy to be delivering this talk, especially in a women's college. It's very pleasing to be a speaker in this very prestigious meeting. I shall straight away go to the talk because we have already lost a few minutes. So I would like to share the slides. Please let me know if there is any issue. Does that work?
Yes, Dr. Swati, it's absolutely fine. You can just go ahead.
All right. So without taking much time, I shall begin the talk. I see some.
Dr. Swati, I'll just, I think there is a drawing appearing somewhere on the screen.
Yes, yes.
So maybe I'll just clear.
All right. This works, I think.
Yeah, this works. Yeah.
Okay.
Thank you. Sorry.
So I'm going to be talking to you in the next 45 minutes or so on the efficacy of carbon membranes for separating mixtures, and focusing mostly on what theory can reveal in such interesting problems. All right, just to give you a few minutes of introduction about what we do at IISER Thiruvananthapuram. We are a multi-scale modeling and computation group focusing on the multi-scale modeling and computation of nanostructures. As far as nanostructures are concerned, microscopic models are not efficient enough and macroscopic models are not accurate enough. And therefore, most often one has to kind of deal with a delicate balance of adopting methodology to the problem in hand very carefully. And that is when the role of multi-scale modeling and computation come into picture. So our group primarily employs multi-scale modeling and computation approaches for looking at carbon nanostructures as well as plasmonic nanostructures. To give you a glimpse of our activities in the direction of carbon nanostructures, we are essentially into designing carbon nanostructures for sensing, separation, and storage applications. Just to give you a feel for a couple of examples in this direction, carbon nanotubes are basically cylindrical structures and their interior spaces are hollow. in principle, you could encapsulate molecules within these hollow interiors, and they could lead to very interesting properties. I mean, confinement has been shown to lead to interesting properties, for instance, in the context of spectroscopy. There have been experiments that have been performed showing that the spectroscopic optical cross sections of molecules that are confined within carbon nanotubes are enormously enhanced. Okay, and therefore, there has been a great interest in understanding the energetics of, for instance, encapsulation of various species into carbon nanotubes. This is an area that we are looking at to be able to propose better carbon nanotube substrates that could be employed for storage applications. In the area of 2D materials, we basically look at graphines, which are newbies in the family of 2D materials, and we also look at a variety of carbon nanomeshes. Carbon nanomeshes are something that I would talk about as we go along. Again, here, the effort will be to design carbon membranes that are ideal for certain specific applications. Now, these applications are primarily involving sensing and separation. I shall touch upon very specific aspects during the talk. Just to give you a flavor of what else we are interested in our group, a lot of our effort has also been in the area of modeling plasmonic nanostructures, primarily for spectroscopy applications. Now, why are we interested in spectroscopy of plasmonic nanostructures? For instance, let's think of a gold heterodimer kind of a system. Heterodimer meaning you have two different sizes of gold particles that are brought in together, and you can think of interesting spectroscopic features associated with such systems. Now, why do we say that they breaking in the system? As you can see schematically here, when you have either two particles with the same composition and different sizes, or two particles with the same composition, as you can see here, the schematic is for the case of two nanorods, one of which is gold while the other one is silver. All right, so in such a case, what happens is that because of this symmetry breaking, both the bonding as well as the anti-bonding mode gets optically active. And therefore, you can in principle experimentally get spectroscopic signatures of these bonding and anti-bonding modes. Why are they relevant? The reason is simple. Analyte molecules, when experimentally probed at the junctions of these nanostructures, you essentially get huge optical cross sections. They are so good that today it is possible to detect single molecules that are trapped at these junctions. And our effort in the group has been towards designing such materials that could lead to enormous optical cross sections to be observed in the experiments. So these are two aspects that our group works on. And as the title suggests, I would essentially in this talk focus on the first aspect, where we look at carbon nanostructures for various sensing and separation applications. The relevance of carbon, of course, dates back to several decades. And we know that there are various allotropes possible primarily because carbon atoms can exist in various states of hybridization, sp, sp2 as well as sp3. Again, this needs no introduction to the audience here. So I'm straight away going towards the 2D membrane systems. Diamond and graphite are the conventionally known allotropes of carbon. But the more recent additions are what we have out here on the slide: graphene, carbon nanotube, and fullerene. Fullerenes were discovered in 1985, carbon nanotubes in 91, and you could just imagine a carbon nanotube as a rolled up sheet of graphene. Graphene is a single layer of graphite. All right. Although graphene was theoretically modeled way back in 1947, the revolution in graphene chemistry essentially came up because of the possibility of isolation of the single layer graphene experimentally in 2004. All right. So now this is again to give you a flavor for the timelines. Now graphene has been shown to be a wonder material with excellent properties ranging from flexibility, transparency, ultra strong mechanical properties, elastic properties, corrosion resistance, electrical conduction, and many such useful properties. All right, which is the reason why graphene is actually referred to as the queen of carbon flatland. And it is considered a wonder material. In the last 2 decades, exceptionally interesting properties of graphene have been demonstrated. But I shall not dwell upon any of these a range of properties, but I shall focus in the talk to only one very important property, which is basically its application in membrane-based technology.
Okay, so one thing is, Kamish, what I also we just sent out a message. This one.
Rajesh, there is some interference from your side.
Yeah, Dr. Swati, please go ahead. I think it's okay.
Yeah. So I am basically focusing on one application of graphene here, which is to do with membrane-based technology. Again, we don't need any introduction to membrane-based technology. All of us are familiar with this idea of, using a separating membrane in kitchens, for instance, right? All of us are familiar with this. But as far as graphene is concerned, it is not going to be extremely useful for any of these applications, primarily because graphene is impermeable to most species. I have just illustrated here a set of molecules and ions that we normally would think of, and you will realize that even proton is impermeable. Except for proton, nothing else is permeable through graphene. Okay, what it means is this. The hexagonal pore is so tiny that except for proton, the pore doesn't let any of the other species to pass through. If that is the situation, then what can we do to essentially use it for membrane-based technology? It seems to be practically not of great use, right? Therefore, attempts have been made to actually modify graphene such that you could very smartly use it for separation applications in membrane-based technologies. Okay, so how does one do this? This is the approach. You basically have to drill pores through graphene to create nanomeshes. Okay, once you drill pores through graphene, you essentially create large-sized pores, which can in principle be allowed to selectively permeate certain molecular species or ionic species through the pores. Now, depending on how you drill pores and what kind of pore architectures that you create in the graphene sheet, you can use it for a variety of purposes. Okay, and typically in experiments, what one does is this. We use a high energy atom beam or an ion beam to drill pores through graphene network as schematically shown here. And one major problem with such an approach is this. Most often, this procedure leads to a lot of defects. All right. And besides the issue with defects, we also have problems in controlling the porosity. All right. Please realize that if I, for example, want to think of separation of molecular hydrogen from molecular nitrogen, just as an example, the pore should be very, very carefully designed such that it allows only one species to pass through while blocking the other. And therefore, any amount of defects or irregularity in the pore architecture is going to cause a lot of problems to us. And therefore, it was felt by researchers that, okay, it is good to have pores being drilled through graphene, but then this is not going to be a viable solution for membrane-based technology. And therefore, alternatives were being explored by researchers. And this led to an interesting idea of actually creating these membrane architectures via what is known as a bottom-up synthesis. If you look at the previous example, the way to generate these nanomeshes is what is known as a top-down approach for creating nanomeshes. Why do we say it is a top-down approach? We have a graphene membrane, we knock out some atoms by using a high-energy atom or ion beam and create nanopores. So this is basically a top-down approach. In contrast to this, this particular way of building up molecules from a small molecular system is what is referred to as a bottom-up approach of building 2D membranes. Okay, so let me just give you an example here. These are basically the materials that you see out here are all what are referred to as graphines, and these are considered new members in the carbon flatland. All right. You can see the timelines here. The experimental realization was achieved in 2010. So they are pretty recent in the members of carbon family. All right. Now, if you look at this example, which is a gamma form of graphene. So the way it is envisaged to be built is this. You consider, you consider hexaethynylated benzene. So basically it's a benzene molecule with all ethynylated groups coming out. Okay, and you can think of doing a cross-coupling reaction on such a system to generate a 2D membrane. All right. So this is experimentally realized. And this procedure of bottom-up synthesis of carbon membranes was suggested to be extremely useful for sensing and separation applications, primarily because using this procedure, we could now control the porosities. We could control the pore architectures, and in principle, it is possible to design a pore system that could enable a specific application for us. All right, so if you already see a plethora of carbon membranes here, it is clear to us that you can form triangular pores, you can form hexagonal pores, you can form rhombic-like pores. And each of them is in principle possible to be used for a specific application. All right, so again, because of this interest in bottom-up synthesis of graphines, a variety of applications have been proposed, starting from energy storage to water desalination to catalysis, especially in the last 5 to 6 years or so. All right, so not only these graphene materials, but a variety of other membranes were also experimentally reported in the last few years. These are again some examples where still-beam based pores have been used to generate these kind of porous architectures. Now they have been designed with specific applications in mind. If you look at this particular example, this is basically a 3-dimensional pi architecture kind of system. So if you look at the triangular pore, you see that there are 3 benzenes which kind of eclipse the triangle. Right? This is slightly in contrast with what we had seen in the case of graphines. Please notice here, these are acetylenic groups which are basically forming the triangle here. But if you have them for benzene kind of structure, then you get the 3D architecture. All right. So I am going to now focus on very specific kind of carbon membranes, which are basically known as graphene crown ethers. And these are crown ethers embedded in graphene architecture. Again, crown ethers are extremely popular in supramolecular chemistry. I'm sure you all have heard about crown ethers. So basically, these are the crown ether architectures. You have 4 oxygen atoms, and then which are connected through the carbon linkages, right? And depending on the pore that you think of, you can have, for instance, 10 crown 2, 12 crown 3, 14 crown 4, 16 crown 5, and 18 crown 6. Okay, the name again is obvious. 18 is the number of atoms in the periphery, and 6 essentially indicates the number of heteroatoms in the crown ether framework. This nomenclature is again very popular from supramolecular chemistry literature. Now the point here is that such crown ether architectures, when embedded into graphene network, is what we call as graphene crown ethers. Okay, and what is so exciting about these graphene crown ethers is this. Experimentally in 2014, Professor Guo and co-workers have actually characterized each of these graphene crown ethers. Okay, these are data from high resolution spectroscopy experiments, which pinpoint to the location of the heteroatoms in these graphene crown ethers. Okay, and this was considered to be a good breakthrough in the design of graphene nanomeshes. And now I shall take you through the permeation process, which is of interest in this particular talk. Okay, we have talked about a variety of carbon membranes that one could think of, ways of designing these carbon membranes, ways of experimentally realizing these carbon membranes. However, one would wonder that why am I so interested in worrying about permeation through carbon membranes? What is so exciting about it? I'll give you a few examples out here. If you think of 2 species, as you can see in this schematic, a pink ball and a blue ball. Okay, you could think of a membrane that would perhaps let in the pink balls to go through, but block the blue balls, which is very commonsensically considered to be manageable, because you know the sizes of the pink and the blue balls. All that you need to do is you need to tailor the carbon membrane such that its pore matches with the size of the pink ball, such that it lets in the pink ball while blocks the blue ball. This is very, very simple to imagine, and therefore this is the most straightforward way of achieving separation using carbon membranes. But today, because of the advancements in both theory and experiment, we have gone way beyond this very simplistic picture. And the literature has interesting reports on a variety of carbon membranes, so to say smart membranes, which can do excellent job in separating very, very intricate species. Okay, and in this talk, I shall give you few examples of what we can achieve by such an analysis. Now you can imagine the next example where you see a red and a green ball, and it's very apparent that they possess the same size. And therefore, can one design a smart membrane that will selectively allow the permeation of red ball while blocking the green ball? This is one of the questions that one could ask. And then in the next level out here, you could see, for instance, I have a 5-carbon chain and I have various possible isomers that can arise from such a 5-carbon system. All right. Can I design a smart membrane that will selectively allow 1 or 2 of these isomers to pass through while blocking the remaining ones? Okay. The next example is in the ladder is even more interesting. Okay. So let's say we think of 2 chiral species, all right, which are enantiomers. Okay. So now these 2 obviously are enantiomers, and therefore it must be very difficult to imagine a membrane that would essentially enable separation of these 2 isomers. All right, it would be very interesting to think of a situation where you use a carbon membrane for separating 2 chiral species. All right, so very recent efforts in theory, for example, have gone into designing such smart membranes which are tailored to actually bounce off one of the chiral enantiomers by a specific interaction that is possible because of the rim species that are out here. All right, I shall touch upon these examples as we go along. Yet another very, very interesting example of permeation through carbon membranes is that of DNA sequencing. All right, DNA sequencing is a very, very interesting process. All of us know, because we would like to know in principle what is the genome sequence that we are all made up of, right? And because of a lot of interest in exploring membrane-based methodologies for sequencing DNA, a lot of effort has gone into understanding approaches for DNA sequencing using graphene membranes. And today, successful experiments have been reported which say that it is actually possible to measure differential current that one gets when each of the bases of DNA passes through the carbon membrane. Okay, and this subtle measurement of the current is what enables the entire DNA to be sequenced using graphene-based technology. And that's extremely amazing to think of. And therefore, if we could actually predict such phenomena, and if we could design carbon membranes using theoretical approaches that could lead to any of these applications, that would be remarkable. That's the philosophy with which we work in this particular area. All right, so I will start again from the simpler examples to the complex examples. So the most straightforward example is the case of a size sieving mechanism. Okay, the name itself is obvious. It is self-explanatory. When we say size sieving, we essentially are looking at sieving by the carbon membrane based on the sizes of the 2 permeating species. Okay, because the red one is hefty out here, red one cannot permeate through the pore, while the blue one permeates through the pore. Okay, this is one of the most straightforward examples of sieving. Okay, now let us try to get a bit more quantitative. All right, so I have talked about graphene membranes. And if you look at this molecular system out here, this is basically a molecular model system of graphene. All right, as you might have already noticed, we had these triangular pore architectures, right? One such triangular porous unit is what I'm considering as a simpler molecular model system to begin with. All right, so now when you have such a molecular model system and when you're looking at a species permeating from one side to the other side, it is essentially like this cat moving across the ring, all right, physically speaking. So now what is the interest in looking at permeation through such membranes? As far as the theory is concerned, this example is basically an illustration of a lithium ion going from one side of the molecular system to the other side. Okay, so now what is the potential for the motion of the lithium ion as it goes through the pore? Okay, a typical potential that is possible for the system is the case of a symmetric double well, as you see here. Okay, why do I say symmetric double well? Again, let me explain this physically. What happens is you have a pore out here and then you have an ion which kind of is favorably bound on the top surface. All right, but there is an equivalent minima configuration on the bottom surface because you essentially have a membrane and you have one species getting bound on one side, the other getting bound on the other side. And therefore, when you have a membrane, you have two equivalent minimum energy configurations on either side. Those two equivalent configurations are what we see here as the two minima in the double well. Now you see that as one goes from one minima to the other minima, there is a barrier. Okay, and this barrier is what characterizes the transition state of the system. Okay, if the pore is very tight, what it physically tells us is this: if you try to put the molecular species that you have in mind in the middle of the pore, it doesn't like it because it's energetically unfavorable for the system. And therefore, you have a high barrier under such a circumstance. While on the contrary, think of a situation where the pore is reasonably large such that it allows a facile motion of the species from one side to the other. In such context, you have what is known as flat potential coming from the motion of the species. Okay, so what it tells us is this: physically, if we want to estimate as to whether an incoming particle goes through the pore, whether it likes it or doesn't like it, is characterized by the potential energy surface that we are seeing out here. Okay, if there is a large energy barrier, then we say that the molecule doesn't like being permeated and therefore it resists passage through the pore. While if there is no energy barrier, it likes to go from one side to the other side. That's the interpretation. All right. So now this process is again familiar to us from what we study in the school and the college times. Okay, ammonia inversion is something that we are all familiar with, right? So ammonia goes from one pyramidal configuration to the other pyramidal configuration via what is known as a planar transition state. Okay, planar transition state is a high energy configuration for ammonia, known to all of us. Now, if we look at the potential energy for the inversion of ammonia from one pyramidal to the next pyramidal geometry, it is essentially of the nature of a double well type. Okay, so what it tells us is this: when we think of permeation through pores, the nature of the potential is very similar to what we have in the case of ammonia inversion. This is again only for us to relate to something that we know. All right. So in our group, we have been making a lot of efforts in understanding permeation of a set of ions, for example, lithium and sodium ion through graphines. Okay, again, the application that we have in mind is pretty obvious. We are essentially thinking of designing materials that could be useful for lithium batteries, right? Lithium ion batteries. So that was the objective with which we set out with, and we wanted to explore how efficient are these graphene membranes to serve as anodes in these materials. All right, and at the fundamental level, if we want to understand this, we have to probe the propensity of permeation of lithium through these triangular pores. So that was the first attempt that we performed on this kind of systems. And the analysis goes like this. We basically construct the potential energy surfaces for the permeation of lithium through these pores. If you now think of pristine graphene, okay, which has very, very small pore size, obviously the lithium ion doesn't like to permeate through the pore, and therefore this should be associated with a very large barrier, as you can see here, which is 247 kilocalorie per mole. But if you now think of graphene or graphdiene, let me again explain the terminology here. When I say graphene, it has one acetylenic unit on the triangular pores. Okay, when I say graphdiene, it has two acetylenic units on each of the triangular pores. Now, because the pore size is large, graphdiene actually facilitates the motion of the lithium ion and it's barrierless. But if you think of graphene, it offers a very small barrier for the permeation of lithium ion. In fact, it is actually comparable to the barrier for ammonia inversion. This is again only for a physical relation between the numbers that we get for the energy barriers in both cases. One has to be careful not to interpret too much into the correlations between the two systems that we are thinking of. All right. So what it tells us is this: the free motion of lithium ion is possible using graphdiene as a membrane materials. Okay, and therefore this analysis, of course, in combination with several other kind of calculations that one would resort to in order to establish this picture, we could show that graphdiene could be an interesting anode material for applications. All right. So I will now come back to the example of graphene crown ethers, which I talked about. Because it is experimentally possible to characterize such porous architectures, we went ahead to model them because it was already experimentally established. And we have shown that such aza crown based graphene crown ethers could be excellent receptors for alkali ions. Again, this is an approach that enabled us to show that it is possible to separate the alkali ions using such graphene crown ether membranes. I will again come back to this in the case of a more systematic example of isotope separation after a few minutes. But as far as the size sieving mechanism is concerned, again, the phenomena is somewhat straightforward to explain. You can explain it based on the matching pore sizes of the membranes as well as the molecular kinetic diameters of the various gas species that you have in mind. Okay, but it is possible to go beyond the size sieving mechanism and design membranes that could essentially have specific affinity to a set of molecules, which would enable permeation of another molecule to pass through. And this is an example which tells us this. If you have nitrogen and carbon dioxide molecules, a conventional mechanism would tell us that nitrogen molecules would permeate through strongly through such a pore while blocking carbon dioxide. But it is possible to think of a membrane that would actually reverse this trend. All right, it all depends upon the kind of design strategy that we have. All right, yet another example that I would like to bring to your attention here is the case of permeation of fullerenes through carbon membranes. Okay, and if you think of, I will come back to the reason as to why we are interested in this, but the problem that we think of is this. We have, let's say, a fullerene molecule. Can we analyze the motion of the fullerene from one side of the graphene membrane to the other side via a situation where the fullerene actually sits in the pocket of this carbon membrane? Okay, this is obviously a high energy configuration, and therefore can one quantitatively estimate whether this motion is going to be facile or not? That's the question that we asked. Now, why are we interested in this fullerene story? The reason is this. Carbon-based nanomechanical oscillators have been investigated in the last 10 years quite well. So this report in the science paper essentially talks about a kind of carbon nanotube based oscillator, wherein if you have a multi-walled carbon nanotube, all right, what happens is that you can in principle have oscillations being set up by pulling one of the inner walls of the carbon nanotube. All right, now it has been found that the oscillations could be attributed to the very weak van der Waals interactions. And that's the most exciting part of the story. Okay, so what was demonstrated was you could actually control the motion of these inner walls of the multi-walled carbon nanotube. Okay, and you could analyze the oscillation. And this oscillation turns, if it turns out to be in the terahertz regime, it's going to be extremely useful because it has been very well known that to have devices in the that can operate in the terahertz regime is extremely important. Okay, so this report essentially talked about the design of a gigahertz oscillator based on such a simple motion of the inner wall of the multi-walled carbon nanotube. Okay, and it so turns out that the entire origin of this is because of weak van der Waals interactions that bind the various walls of the nanotubes. All right, so this kind of triggered to us that can one design such nanomechanical oscillators based on graphenes. Graphenes have been explored well in the last 5 years in our group. So that was a natural question to ask. So the question is, can we propose designer strategies for eliciting oscillatory response by analyzing the rattling motion of fullerenes through various graphenes? Okay, and the literature had actually oscillators primarily with C60 because C60 is a very well studied system. But today it is possible to actually prepare smaller fullerenes in good synthetic protocols, and therefore can one decide oscillators that can go beyond C60. Okay, and one of our interests was actually to propose optimal empirical potential parameters for graphenes, which were actually non-existing in the literature. And possibly such parameters, if developed, could be very useful for any force field calculations using graphines. That was yet another objective with which we set out to do this. And therefore, what we did is the following. We wanted to come up with optimal empirical potential parameters, and therefore we explored two kinds of potential approaches. One is the standard Lennard-Jones potential that is familiar to all of us. Then we looked at the improved Lennard-Jones potential because we are interested in the energy barrier estimation. What happens is that if you have a simple Lennard-Jones expression, it overestimates the repulsive part of the interaction, and therefore the barriers turn out to be huge, which sometimes will be unphysical. And give you a few based. So here are the gamma graphene and gamma. You can and gamma of graphene. 4 acid and 6 acid. Around graphene. These were kind of analysis we performed and potential relate fitted, which would enable to come to graph. Actually gave us the accurate fit parameters that would reasonably well reproduce the electronic structure data. And please remember that these calculations were done at very, very low computational times compared to the electronic structure data. And therefore, the agreement is remarkable. Using such an approach, what we have shown is this. We could actually come up with 3 interesting systems, C20 at gamma graphene 5, C42 at gamma graphene 6, and C70 at rhombic graphene 5. And each of these oscillations were shown to be in the terahertz regime. And this is extremely interesting from the point of view of device applications. And therefore, this work drew a lot of attention. It appeared on the Young Scientist special issue of JPCC. Now I shall switch gears and move on to the very fascinating example of isotope separation using carbon membranes. Okay, so as I'm going towards more complex examples, please notice here that these 2 balls are of the same size, yet we would like to think of a membrane that can enable only one of the species to pass through. Okay, now how does one achieve this? Again, we employ what are known as graphene crown ethers in this particular case to show that it is possible to actually separate helium-3 from helium-4 using such membranes. Okay, so the procedure to follow is very similar to what we did earlier in the case of fullerene and lithium-ion example. So you consider the motion of helium-3 and helium-4 through the membranes like this, generate the potential energy curve, and then you realize that if the particle is a kind of classical particle, what will happen is if the energy barrier is large compared to the energy with which the particle comes, the particle would never permeate to the other side. All right, that is a very classical way of looking at it. But now if we have a quantum mechanical particle, we all know from basic quantum mechanics that if the potential energy is large in comparison with the incoming energy of the particle, even in such a scenario, you can have a non-zero probability of particle being found on the other side. Okay, which is primarily attributed to the quantum mechanical tunneling effect. All right. So in this particular case, we essentially exploit the advantage of the quantum mechanical features of helium-3 and helium-4 and use tunneling as a mechanism for achieving separation of helium-3 from helium-4. All right. So this is the classical example wherein you have a step function for a transmission probability. Physically speaking, what does a step function tell us? If the energy of the particle is less than a given value, the particle is rejected. If the energy is greater than a given value, the particle is let in. All right. But if you have a quantum mechanical particle like helium-3 or helium-4, you please realize that this curve essentially tells us that even if the energy of the particle is less, it can in principle have a non-zero probability of being found on the other side. All right. So what we did is this, we have generated the potential energy profile, but now we have to be careful because we have to explicitly calculate quantum transmission probability. And in order to do this, we have adopted what is known as an Eckart potential formulation, wherein the potential that we saw here schematically was basically approximated to be an Eckart function. And this enabled us to analytically arrive at the transmission probability. Now temperature can be automatically brought into the picture by way of Maxwell-Boltzmann distribution again. So you can consider thermally weighted transmission and selectivity. Okay, so then one employs the methods of transition state theory to calculate these transmission probabilities for helium-3 and helium-4 to pass through these graphene crown ether membranes. Okay, you can already see that this is the data that we get, which means helium-3 basically has a obviously larger deviation from the classical picture on either sides, which you can see from the green trace out here. Okay, and now if you probe the temperature effects, the transmission plotted as a function of temperature clearly tells us that if you had looked at temperatures below 40 Kelvin, you can essentially see the separability of helium-3 from helium-4. All right, that's essentially because of quantum mechanics being in action. Okay, and these effects obviously die down in the high temperature limit because we essentially retrieve the classical mechanics limit. All right, so this is a demonstration of a smart membrane that can essentially do the job for us to separate helium-3 from helium-4. And the mechanism of separation is what is known as the tunneling of quantum mechanics. All right. There are a couple of more examples here which have been reported by other groups. Water desalination is one extremely popular example because there has been a lot of interest in actually designing membranes that would enable us to obtain pure water on the side, on the one side, while blocking the ions on the other side. All right, even in this direction, theory has contributed significantly with the design of smart membranes. This is a recent report again. And this is an example that I was very keen on sharing with you. So this is an example, again, a theory report wherein the approach is this. It is again a design of a smart membrane wherein the membrane pore has what is known as a molecular doorman. Okay, so this is the guy who essentially bounces off one of the chiral isomers while allowing the other chiral isomer to pass through. Okay, and the way the smart membrane is designed is like this. So if you have at the pore of the nanopore, if you have the rim atoms being consisting of an OH group like this, what would happen is you could think of forming a very stable configuration with one of the chiral isomers, while with the other isomer, you could think of having an unfavorable interaction. Again, this is a careful design strategy which enabled this guy, essentially a molecule that is selectively chosen to bounce off one of the chiral enantiomers, okay, while allowing the permeation of the other. This is the same example schematically shown here with the molecular structures. So this is another example where graphene nanoflakes have been used to achieve separation of D-leucine from L-leucine. Okay, now how does this work? You basically consider a multi-layer architecture, and if the layers are arranged such that the rotational angle between them is 0 degrees, okay, it's an achiral system, and therefore it doesn't have any selectivity for the two enantiomers. But if you design the graphene multi-layer membranes in such a way that there is a rotational angle of 60 degree between the two units that are consecutively there, then the membrane becomes selective for one of the enantiomers. All right. So this is the result of such a study. These are basically molecular dynamic simulations which showed that when you have the multi-layer graphene membranes chosen such that there is a 60-degree rotational angle, you could achieve an excellent separation between L-leucine and D-leucine. All right. I will come back now to the last example that I had in mind, which is the case of DNA. DNA, of course, all of us know it is considered the secret of life. The code is written in terms of bases and so on. So in this context, the nanopore-based technology has again become relevant with regard to DNA sequencing applications. All right. So there are studies which show that you can in principle measure the ionic current that comes up as each of the nucleobases permeates through a graphene membrane. These are real experiments that were reported in the last few years. All right. So you can see the current versus voltage profiles out here. And in the process of permeation of these DNA molecules, you can measure the differential current experimentally. All right. And this in principle enables sequencing of the entire DNA. And that is remarkable because if you look at this picture, it is very clear that when the applied bias is 0.8 volts, the permeation is actually very slow. While when the applied bias is 4.3 volts, the molecule permeates very strongly. All right, and therefore they could analyze the translational time and all the important characteristic properties that would enable the characterization of the entire sequence of DNA. All right, this is again somewhat refined by using a multi-layer graphene strategy, but the philosophy of the approach remains the same as what we talked about. All right, so I would like to close the lecture by thanking the organizers again for extending a kind invitation. And thank you all for your patient listening. I would like to thank my group and the funding agencies for the kind support. Thank you once again.
Thank you, Dr. Swati, for such an insightful lecture. So I think most of us would be really excited about these new prospects that nanotechnology has to offer. So we'll just wait to see if a few questions pop up in the chat box. Let me put across a question to you on my part, Dr. Swati. So you did these molecular modelings, right? So they were pretty large structures, even though they were models. So actually, I saw you mentioned some DFT calculations out there.
Yes.
So was it actually possible to optimize those structures when you say do the potential energy surfaces?
Yes. So the point is this: when we do DFT, we actually do it on smaller molecular model systems.
Yeah.
And then what we do is we do a fitting with empirical potential parameters. All right. And get the best fit parameters, use them for modeling larger systems. That's why I showed the algorithm, which we use to do this fitting exercise. Otherwise, it is almost difficult to.
But the models themselves, they are optimized structures.
That's right. Yes.
Okay. So even then, they're pretty large structures. So it's good that
not really around 100 atoms.
Around 100, yeah, and we are just talking about carbon atoms here, so mostly.
Yeah.
So
yes.
It should.
Yes.
Okay, and just from an experimentalist point of view, is this like the permeable membranes are allowing, say, salt water to be separated from fresh water and so on. So and even that permeability of one chiral molecule over the other. So just asking as an experimentalist, is there an experimental analogy, like is there a scope of that being experimentally realized in the recent future? How far have the scientists actually progressed on this experimentally?
Okay, the desalination aspect has been experimentally demonstrated.
Okay.
Okay, there have been some new reverse osmosis membranes. In fact, it has come out as a technology as well.
Yeah, reverse osmosis is now very
so graphene based membrane
technology.
technology is also shown to lead to these similar findings.
Okay, so there is a good probability that even the prospect you described about the chiral molecules being separated, so that is also possibly something we'll be looking forward to.
Yes, that is yet to be realized in the experiments, but we hope that it will be done soon.
Okay. Okay, so we have a question from one of our participants, Priti. So she's asking, say, for such a big molecule, only MD is sufficient, or do we need some QM/MM calculation?
Oh, we definitely need some calculations at the QM level, because what happens is even if the system is large, the permeation is actually through the pore. So the bottleneck in the analysis is actually to be able to model the permeation through the pore. Okay, and there quantum mechanics does become important.
Okay, and what software do you use for this? That was another question. The same.
So some of those quantum calculations are all done using Gaussian electronic structure, conventional.
Okay, you just use Gaussian, yeah. And okay, I'll just wait a few seconds to see if we have more questions on this. And Dr. Swati, just one thing that interested me early on in the slide. So this fullerene structure, it has this buckyball structure. So as far as I know, so you call it it is called a zero-dimensional structure. Can you just elaborate on that?
Yes.
So why it's called 0D?
0D.
It's interesting to hear that.
Okay, 0D because there is a confinement of electrons in all the Cartesian directions, X, Y, and Z, because it's a very small spherical ball. If you think of, for instance, a carbon nanotube, okay, it's a very long cylindrical structure.
Yes, absolutely.
Okay, and that is effectively one-dimensional. Why do we say one-dimensional? Because there is confinement in the other two directions.
Okay, and here it is confined in all directions, so it is essentially a
0D.
Zero-dimensional structure.
In case of graphene, it is a two-dimensional structure, so the confinement is along one of the dimensions.
Okay, yeah, yes, and that graphene, the sheet was recognized only in 2004, so that is a pretty new thing. Okay, there is just another question, the last one I think for this session. Dr. Swati, so Dr. Anup, I think Anup Kosha, one of our participants, is asking, does bacterial DNA, I'm sorry, I don't think this question is related to your lecture, and I'm not sure what the question is actually, so we'll just leave it at that, right? And thank you, Dr. Swati, for giving us such an interesting lecture. And as we just said earlier, we would have to like you present your talk sometime even in the future in our university premises, if that is possible anytime in the future. Sure. So thank you for joining us, and it's been good having you here, and thank you and have a good day.
Thank you.
Thank you,
I'm
Dr.
stopping
Swati.
my screen share.
Yeah, that's absolutely fine. Yeah, you can take your time. And I think I should pass over the next session to Dr. Nandi, the co-convener of this webinar, to carry on with the next technical session. Dr. Nandi.
Very good afternoon again. I think I am audible. So I think, yeah, Dr. Guillaume Bansa is already joined. So yeah, thank you, Guillaume. Okay.
Do you hear me?
Yeah, you are audible.
Okay. Perfect.
Just if you want to check whether your slide is presentable or not, you can do now. Before.
Yes.
Just share your slide.
Is it working? Or?
Yeah, it's fine.
Is it fine?
Visible. Yeah, it's visible. Okay.
Fine.
So yeah, let me start. So good afternoon, everybody. In this session, we will have two eminent speakers. One is Dr. Guillaume Vansay from University Paris Sud, and another he already joined, Dr. Debabroto Maiti from IIT Bombay. So it is my pleasure to introduce Dr. Guillaume Vansay, who was born in Lyon, is graduated 2002 from the École Suprême of the Chimie, Physique, Electronics de Lyon. During his period, he spent 1 year in the Depot Pharmaceutical Company and working under the guidance of Dr. Patrick Weiss Lamb with the copper catalyzed cross-coupling between boronic acid and NH-containing substrate. In 2002, he finished his MSc and he joined in the University Lyon with the same group for the PhD with Professor Marco Schiafolini. In 2005, under supervision, he completed his PhD. And during the 2005 to 2006, he did his postdoctoral work at Colorado State University with Professor Robert M. Williams. And then he moved to France in 2007 and in the group of the Professor Max Malakari and Professor Lewis in the University of the P. Marie Curie and studied the anionic radical tandem reaction. Finally, in the 2007, he awarded in the CNRS researcher in the ICMO of the University Paris Sud, which is known as University Paris-Saclay. And in the 2011, he started his independent research program towards the synthesis of the application understanding unusual reactivity of indole nucleus. He obtained in 2018 as an Advanced Researcher Prize from the Organic Division of the French Chemical Society. He was promoted to the Director of the Research CNRS in 2019. With this brief introduction, I would like to Dr. Guillaume Vansay to deliver his speech. Thank you.
Okay, thank you very much.
Guillaume, yeah.
So everything is fine. I can. You hear me on the same slide, I guess.
It's visible and you're audible.
Okay, so thank you very much, Raj. I'm really grateful to have been invited for this symposium, international symposium. So, and I would like to thank you for this invitation, and I would like to thank in particular Raj, Dr. Raj Kumar Nandi, which I know very well. So today I will talk about the aromatization of indole for the total synthesis of natural products. So in our group, we are interested in the aromatization of indole to transform a flat aromatic heterocycle to a three-dimensional structure of interest for drug discovery, but also for the total synthesis of some natural product. So just to start, a short reminder about the reactivity of the indole nucleus. The indole nucleus is a highly nucleophilic entity. It reacts with electrophile by the C3 position of the enamine part of the indole nucleus. So if you have an indole on an electrophile, you'll form a new bond between the indole and the electrophile. You'll get to this intermediate. If the R group is a hydrogen, you have a aromatization reaction and you get an electrophilic substitution. But if the R group is not a hydrogen, this iminium could be intercepted by your nucleophile to get to this compound, which would be desubstituted, or you can have the migration of the R group from the 3 position to the 2 position, and you'll get these 2 substituted indole. So, in our case, in our group, instead of using the innate nucleophilicity of the indole nucleus, we try to do an unpolling of the indole nucleus. In other words, we try to reverse the polarity of the indole nucleus at the C3 position to add nucleophile at the C3 position. So I'll show you some examples of what we have done in this area. I have to notice that there is a nice highlight in the literature in OBC about the electrophilicity, which was qualified as the dark side of indole chemistry by Marco Bandini a few years ago. So few methods that we develop to do some aromatization of indole nucleus is one of them is based on radical chemistry. What we wanted to do is to generate radical radical species in oxidative condition. So once you generated this radical here, it could add on the C2 position of the indole, you form a new bond. At the C2 position, you get a radical at the C3 position. Since you are in oxidative condition, we can imagine to oxidate this radical into a carbocation. And instead of eliminating this proton here to rearomatize the indole nucleus and to have a functionalization of the C2 position of the indole, what we wanted to do is to intercept this carbocation by a nucleophile to get to this three-dimensional indole here. So we were able to do that. If you take this N-acyl indole with a nucleophile on the linker on the C3 position, like carboxylic acid, alcohol, or tosylamide, you can take the Langlois reagent, which is this 3,4-methylsulfinate here, oxidize it with ferric ammonium nitrite. So you oxidize the Langlois reagent into a CF3 radical when you liberate sulfur dioxide. So you generate this CF3 radical, 3,4-methyl radical. As I said before, it could add to the C2 position at a new carbon-carbon bond. The radical could be oxidized by CAN into a carbocation. And you can intercept this carbocation with the internal alcohol, tosylamide, or carboxylic acid. And you obtain this 3,4-methyl spirocyclic indolene in a quite good yields with a high diastero selectivity because the CF3 and the nucleophile oxygen or nitrogen are trans to each other. We get several X-ray structures to prove this stereochemistry. We can also do the same with a phosphonyl radical. You take a phosphate, you oxidize it with manganese acetate. You get this phosphoryl radical, then can add to the C2 position. And as before, the radical is oxidized in a carbocation, intercepted by the internal alcohol, and you get this phosphonospiroindolene. Phosphor and oxygen are trans to each other once again. But in this methodology, you need to use a stoichiometric amount of oxidant, manganese acetate in this case, or ferric ammonium nitrate in the case of the Langlois reagent. So we were interested recently by the rediscovery of electrochemistry in organic synthesis. So we buy this apparatus, this electrochemical apparatus, which is getting really popular now. And we try to oxidize an indole, an acyl indole, in presence of methanol. So we put some current in it, and we were able to obtain several examples of this bis-methoxylated indolene, in which the two methoxy are mainly trans to each other. So what happened is that at the anode, you oxidize the indole, the C2-C3 bond of the indole, this bond here, into a radical cation, so which become electrophilic. A methanol, which is nucleophilic, could add to it. So it could add to the C3-C2 position. Then you get a radical, could be oxidized at the anode again into this iminion, which is again electrophilic, could be intercepted by this methanol, which is nucleophilic. And you get this methoxy, a large number of this dimethoxy indolene. You can use another kind of nucleophile instead of the methanol. You can use a nitrogenated nucleophile like this trimethylcyclic azide, and at the end you get this azidoindolene. They are mainly the two azides are mainly trans to each other when you have a monosubstituted indole, but when you have a cyclic 2,3-D substitution, the azides are cis to each other. You can also do this reaction on a quite complex substrate like this one here. So once you get a bis azide, you can do some functionalization reaction, like reduce this two azide into a bis amino indolene, like here. You can do also a quick double quick reaction with like a Wisgen cycloaddition, and you get this two bis triaziol compound at the end. So another electrochemical reaction that we developed is the synthesis of bromopyrroloindolene from tryptamine or tryptophan derivative. These compounds are really important building blocks for the total synthesis of peptidic natural product or a compound of interest. So in this case, we don't oxidize the indole at the anode. What we do is that we oxidize magnesium bromide, the bromide of magnesium bromide at the anode, into an electrophilic bromine, maybe Br2, for example. This Br2 then react with the indole nucleus. You form this bromonium ion, which will be opened then by the nitrogen or oxygenated nucleophile to get to this furanoindolene or bromopyrroloindolene. So another reaction that we develop, and Raj actually works a lot on this reaction, is to turn the nucleophilic indole into an electrophilic indole. Was inspired by the work of a Japanese group from Nakatsuka. What we did is a non-usual hydroarylation of an acyl indole with electron-rich arine. So the arine, electron-rich arine, you can use all the example you've seen here, will add to the C3 position of the indole, which usually is nucleophilic, but in this case is electrophilic. So this arine add at the C3 position of the hydrogen here, you'll find it at the C2 position. So this reaction is a really broad substrate scope. You can do an intramolecular version of that. You can also, so in all this example, you have a substitution at the C3 position, so the arine add at the C3 position, but when we don't have any substituent at the C3 position, the arine add at the C2 position. And so this reaction is mediated by iron chloride, but you can also use triflic acid instead of iron chloride. So what happened here in this reaction? After sometimes we think we determine what happened here. I just explained the case of iron chloride. So when you have an acyl indole and you add iron chloride, the first thing you do is you form a complex between the acyl indole and the iron chloride. And in this case, the lone pair of the nitrogen, instead of being delocalized onto C2 and C3 position, is more delocalized on the carbonyl position with the iron chloride attracting it. So then the C3 position is getting less nucleophilic than before. Then we do this.
Excuse me, sorry for interrupting, Guillaume. Can you use the pointer on your screen?
You don't see the pointer? Okay, I thought it was.
In fact, we are just viewing your computer screen. When there are two slides parallelly.
Okay, so, you don't see my pointer?
No, we can't see your pointer, as well as we can see the two slides. We can see your only computer screen, not the other things.
Okay, I don't know.
If you use the mouse on your screen, it's fine. We can see it.
Is it better
now? Yeah, now we can see.
Okay. Okay, sorry, I missed because I have two screens on the. Okay.
Is it possible to minimize the upcoming slides?
I don't know.
Okay, then you can continue. It's fine.
So yeah, because.
Okay, you can continue. Thank you.
Okay. So sorry. Okay, I thought I was using the pointer, but okay. So as I was saying, yes. So you form this complex N-acetyl indole with iron chloride. So the lone pair of the nitrogen is not delocalizing anymore on the C2, C3 position. So the C3 position here is now not nucleophilic as before. On in other hand, we are using iron chloride, but we don't use it under argon. We use it under air. So there's probably some hydrogen chloride that is formed, a proton that has formed. So it's probable that this proton will activate the C2, C3 bond. In this case, the C2 position is probably the more nucleophilic. So you get a carbocation at the C3 position, and then it's like a Friedel-Crafts reaction. The electron-rich arine adds to the C3 position of the indole. You form a Wheeland intermediate, and after rearomatization of this Wheeland intermediate by expulsion of a proton, you get the hydroarylated compound. So the proton then that you expel in a stoichiometric manner will then go back to activate another molecule of N-acetylindole activated by iron chloride, and you get this reaction to go. So then I've shown you what happened with arene nucleophile, but what happened with if you replace the arene nucleophile aromatic compound by a double bond, like this intramolecular reaction with the terminal alkyl that we wanted to do, or the reaction with allyl silane, for example, would we obtain this 3,3 desubstituted here indolene? The answer is no, but something happened. Something really interesting happened. For example, when you use this terminal alkene linking to the indole by a 3-carbon linker, we observe a formal 2+2 cycloaddition, and we obtain this pure indolene that has a cyclobutane. And we get X-ray structure again to prove our structure. So it's what happened exactly? I'm not sure it's a true 2+2 cycloaddition, but anyway, it's a really interesting structure. And again, when we use allyl silanes, the allyl silane add into the N-acetyl indole, but not only once, but we get the addition of 2 allyl silane, which was not what we expected. What happening again here? In this case, we don't have any proton that are formed during the reaction, but we instead we generate during the reaction 3-methylsilyl cation that could probably activate the C2C3 bond to make this carbon-silicon bond on the carbocation at the C3 position. Allyl silane could probably add on this, and then you generated again the 3-methylsilyl cation. I have the reaction to go. So then once this allyl silane adds here, you have this carbon-silicon bond that could probably be oxidized by the iron chloride to form an iminium on which a second molecule of allyl silane could add. So from this bis-allylated compound, trans when you have the 2 allyl trans when you have only one substituent at the C3 position of indole, or the alleles are cis when you have a cyclic 2,3 desubstitution of the indole, you can do wind closing metathesis on this subset and get some interesting structure. Then another reaction that we wanted to do on this substrate was cycloaddition. So we get a collaboration with Xavier Moreau at the University of Versailles, Vincent Coeffard at Nantes, and Isabelle Chatenier at Rouen in France. What we wanted to do is to use this dienal in presence of a proline catalyst to form this trienamyl intermediate and to have a 4+2 cycloaddition, that's another type of cycloaddition, to get to this structure in presence of iron chloride to form this N-acetylindole activated by iron chloride. So when we mix everything together, again, we have some reactivity, but we never obtain this compound. And I have to say that proline doesn't play any role, so we remove proline. Instead of the compound, the structure that we were expecting that I showed you before, we obtain this tetracyclic fluoroindolene. So it took some time to figure out the structure of this compound and also what happened here. So what we think happened is that there's first of all an interrupted isonazarov cyclization. So the dienal is activated in fact by iron chloride. You form a cation here, and then you have a co-rotatory cyclization to form a carbon-carbon electrocyclic cyclization to form a carbon-carbon bond here. You have here this oxyallyl cation. You can draw this mesomeric form here, and this is a dipole that looks like a dipole. So you can do a 3+2 a formal 3+2 cycloaddition between this dipole and the N-acetyl indole activated by iron chloride. So the C2 position, which is the more nucleophilic as I showed you before, here could add to this carbocation position, and the oxygen could add to the C3 position, which is the electrophilic on the indole nucleus. And you get, as a major compound, this cycloadder. I have to say that we always observe a little bit of the other Weggio isomer of the cycloaddition. So then another reaction that so this reaction was really interesting. So we wanted to switch from the indole, dipolar to another double bond, like for example, this alkylidene oxindole. We wanted to see if we can do another 3+2 cycloaddition. Actually, once again, something happened, but not what we expected. What we obtained is this cycloadduct, the cycloadduct of a 4+2 cycloaddition. So interestingly, what happened again? So as before, we did probably the interrupted isonazarov cyclization. You form this oxyallyl cation, but this time, before this react with this double bond, you have elimination of a proton, and you form this cyclopentadienol compound, which could react in the 4+2 cycloaddition with this double bond, and you'll get this cycloadduct. So really interesting structure. So then again, we wanted to switch from this alkylidene oxindole to this kind of structure. This can be immunostyrene to have a 4+2 cycloaddition with between the cyclopentadienol and this double bond. So the goal was to obtain this compound. Again, we didn't obtain this compound, but this interesting heptacyclic structure. So we never obtained what we were expecting. So what happened again in this case? What we think is that actually the 4+2 cycloaddition between this diene and this double bond really happened, and you form this compound, but that this compound rearranged into this heptacyclic piperidine. How does it work? So to prove that, in fact, we generated a cyclopentadienol another way by oxidation of this cyclopentadiene ferrocenium in presence of air. So this is a known method to generate this dienol. In this case, when we generated this compound this way without substituent on this position, we actually observe this disalder cycloadduct. And interestingly, when you add acid chloride, this compound could be converted in a low yield, but to the same kind of compound that we obtained before. So the difference here is that you have substituent in this position, and you don't have substituent here. That's why we can isolate this compound in the bottom arrow. So what happened? What we think happens, and so we conduct the reaction in hydrogen chloride. The alcohol is probably protonated by the acid. You form a carbocation, which will be kind of stabilized by the double bond here. So the nitrogen of the imine will attack this carbocation, will form this iminium, and then rupture of a carbon-carbon bond. You get this allylic cation, which will be attacked by this aromatic bond here, and then it will lead you to this heptacyclic structure that we obtained. So really interesting chemistry. So I told you that we wanted to do total synthesis. So now I'll try to talk about total synthesis on the aromatization of indole. So, in fact, we are interested in natural products that contain this benzofluoroindolene framework here. So you have the indolene in blue and the benzofuran part in red. You can find this motif in several natural products, such as the most famous one is probably diazonamide H, which is a really potent antitumoral agent, and which has been the target of several total synthesis starting from 2000, but the first one has been done by Casey Nicolaou. In our case, we were really interested by the total synthesis of Wacalgin A and biplophylline, which is this two compound on biplophylline. As you can see, is a quite complex natural product. should be noticed that you also have phthalate, which is the only one of this family in which nitrogen and the oxygen are not on the same carbon, contrary to this structure here on all the other natural products. So from a biosynthetic point of view, how this benzophenolidine structure is made, it's probably the oxidative. There's no proof, but it seems really logical that it's the oxidative coupling between the indole and the phenol. So in this case, if you do an oxidative coupling between these two compounds, you'll form a carbon-carbon bond between the C3 position of the indole and the ortho position of the phenol. And then the oxygen of the phenol could intercept this imine, and you'll get to this benzophenolidine structure. So actually, Patrick Aron in 2003 did the total synthesis of diazonamide using a biomimetic or bio-inspired oxidative coupling of indole on the phenol. So what he did is he took this compound, which is derived from a tripeptide containing the indole of tryptophan and the phenol of a tyrosine, treat this compound with this diacetylthiodobenzene, which oxidizes specifically the phenol into an electrophilic species, a phenoxylium species. The indole, which is nucleophilic, will attack this electrophile, form the carbon-carbon bond, and then go to the benzophenolidine part of diazonamide. So this is a really nice reaction, really powerful. Unfortunately, it's a little bit substrate dependent, because when we try to do it in an intermolecular way or with a really simple substrate, all we get is a really complex mixture of compound with over-oxidized compound. So we try at this point to develop another oxidative coupling between indole and phenol. One reaction, for example, that we develop is the use of iron chloride to form the N-acetyl-indole activated by iron chloride, as I showed you before. And we talk in the other hand a quite electron-rich phenol with a para-alkoxy group. So we use iron chloride on DDQ. So the DDQ will oxidize the electron-rich phenol into this phenoxyl radical activated also by iron chloride. This radical will add to the C2 position of the indole. You form a carbon-carbon bond here. And then the radical that we form here could also be oxidized by DDQ. And then this oxygen will end up attacking this, the carbocation here, and you get benzophenolidine of the type of phthalate, in which the oxygen and the nitrogen are not on the same carbon. I have to say that after our work, there was an electrochemical version of this reaction by Professor Aiwenley, and Professor Yang-Sinja also used this concept to do the total synthesis of phthalate last year. So we did not use this reaction ourselves to do total synthesis, because when we tried to use it, there was some limitation. That's why we developed another reaction based on the oxidation of indole with aniodine succinimide, which is iodine electrophilic reagent. So the indole, which is nucleophile, will attack the electrophilic iodine to form this iodoindolinine. If you treat this iodoindolinine with soluble silver salt, you'll get the precipitation of silver iodide, and you'll form a carbocation at the C3 position of indole that could be then attacked by a phenol. So the phenol will attack by its orthoposition to this C3 electrophilic position of the indole, and the oxygen will also intercept the imine, and you'll get several benzophenolidine here, which are isomers to the one we made before. So it's really interesting, but because this methodology, we use it to make compounds which were really close to the natural product voracalgine. These two compounds, as you can see, they have 6 of the 7 wings which were needed to make voracalgine A. The problem is that for that we use palmitoxy phenol, which is not the phenol that we need to make voacalgine A. To make voacalgine A and then bipleophilin, we need to do this reaction with a catechol. So what happens when we use a catechol in this reaction? We don't obtain the basoferrandolene that we need to make voacalgine A or bipleophilin. What you obtain this is this deoxazino, this basofluoroxazinoindolene, where you form 2 carbon-oxygen bond between the C2 and C3 position of the indole on the catechol. This is really interesting structure, but that's not what we needed to go to bipleophilin or voacalgine A. So we again had to develop another reaction, another oxidative coupling between indole and catechol. So we started to collaborate with Laurent Evano and Erwan Poupon that work at the same university as us, but at the School of Pharmacy, and we are at the School of Science. So there's really specialty in biomimetic synthesis. So what's the biosynthesis of voacalgine A and bipleophilin? It's probably the oxidative coupling between this bis-hydroxycarboxylic acid and pleocarpamine, which is a natural product. So the catechol of bis-hydroxybenzoic acid is probably oxidized into an orthoquinone. The indole, which is nucleophilic, will attack at this position of the orthoquinone. You form a carbon-carbon bond, and then the oxygen will attack the C2 position to make the benzoferrandolene of voacalgine A. Then another oxidative coupling between voacalgine A and another molecule of pleocarpamine should get you to bipleophilin. From a synthetic point of view, the reaction between indole derivative and paraquinone are known also to form benzoferrandolene. That's work of David Chen, for example. So what we do from our part is to take a catechol, this bis-hydroxybenzoic derivative. So we didn't took the carboxylic acid itself, but it's methyl ester. So we take this catechol and indole, and we twirl several oxidants to get to this benzoferrandolene. So we twirl several oxidants that are not oxidize catechol into orthoquinone. We found that silver oxide was the one that we needed, and we were able to get three or four benzoferrandolene substrates here. So as you can see, the yields are not great, but at least we have accomplished what we wanted to do. The oxidative coupling between a catechol and the indole that gives you access to benzoferrandolene. So we are quite happy about that. So you form the catechol and the indole probably attack at this, do a kind of 1,6 addition at this position. So it worked with the methyl ester, but to get to bipleophilin, we needed to do it on the free carboxylic acid. So we replace the methyl ester by the free carboxylic acid. And at this one, once again, we were surprised to obtain something that we did not expect. We don't obtain the benzoferrandolene part, but we obtain this isocomenoindolene part, which you can also find in bipleophilin. It's really interesting. In this case, we probably found the orthoquinone, but this time the indole attack at this position as a 1,4 addition. So as you can see, the scope of this reaction is broader. We really had many more examples, and yields are also much higher. So what is this difference of selectivity? What we think, we have no proof of that, it's just a proposition. What we think happened is that in any case, the 1,4 addition of the indole into the orthoquinose is favored. So this green arrow. So in this case, when you have the carboxylic acid, you form this carbon-carbon bond, and you get an iminium. In this case, this iminium could be intercepted really easily by the carboxylate, the carboxylic acid, to form the carbon-oxygen bond, and you get to isocomenoindolene. But if you have the methyl ester, to intercept this iminium by the oxygen of the ester, you need to break a carbon-oxygen bond, which is not so easy. So this addition is probably reversible, and you can, so you regenerate the orthoquinone and the indole, and you can at this point have a little bit, some 1,6 addition by this red arrow. You form, in this case, this intermediate, and in this case, the iminium could be really intercepted easily by the oxygen coming from the orthoquinone, and you'll get to benzoferrandolene. So, okay, we are able to make in one hand a benzoyl-threondoline, on the other one an isocomenoindoline, which you can form both into the natural product by propylene. What about having these two moiety in the same molecule, in the same compound? It's totally possible if you start from isocomenoindoline, this isocomenoindoline, you oxidize it with silver oxide from the orthoquinone here, add indole, and you have the same reaction between the indole and the catechol that gives you access to this the benzoyl part on this eta-cyclic compound, which is really the core structure, the heart of bipyrophylline. It's even better. You can start from the bis-hydroxybenzoic acid itself on the needle. This time, instead of using an excess of the catechol, you use an excess of the indole, and we mix all that together with silver oxide. Get in one step the same heptacyclic compound with a benzoyl and an isocomenoindoline. So we have the methodology to make bipyrophylline, but we don't have the starting material. To make a bipyrophylline or voacalgine, you need pleocarpamine, which is a natural product that, as I told you before. To do a total synthesis of this compound is much more complicated than it looks like. I will talk about that in a few moments. But in 2016, when we did this work, we didn't have this compound by synthesis. But what was possible that it was to extract it from the plant, from the natural source by Laurent Evano and Erwan Poupon. So we can have about 100 milligrams of this compound by extraction. So we take natural pleocarpamine, the bis-hydroxybenzoic acid, add silver oxide, and we were really happy to obtain voacalgine A, the natural product. So we have to rewrite the structure of voacalgine A at this point. It's not a benzoyl-threondoline here as we saw before. It's an isocomenoindoline, which makes sense when you look at the methodology that we developed before. So then we have voacalgine A. Can we make bipyrophylline? Yes, it's possible. You can isolate voacalgine A, add more pleocarpamine, more silver oxide, and you get a bipyrophylline. So with a really, really modest 3% pH from this bis-hydroxybenzoic acid and pleocarpamine. So from voacalgine A, you oxidize the catechol into an orthoquinone, and then pleocarpamine adds into it. So we are really happy because we made the first synthesis of bipyrophylline. Anyway, it was a semi-synthesis, it was not a total synthesis. We were still interested to do a total synthesis of bipyrophylline, but to do that, we need to do a total synthesis of pleocarpamine. And which is really interesting is that, sorry, I lost the mouse, is that pleocarpamine is, from pleocarpamine, you can not only do access voacalgine or bipyrophylline, but you can also access several other bis-indole alkaloids like fumocoline, pycnanthinin, goniomedine, etc., and several others. So we wanted to do a total synthesis of pleocarpamine. Again, what is the biosynthesis of pleocarpamine? Because we want to inspire our work from the biosynthesis. So pleocarpamine is a monoterpene indole alkaloid, which is a big family of 3,000 compounds that are isolated from tropical plants. They all have in common strictozidine as a biosynthetic precursor, which comes from the enzymatic catalyzed peptide spangler between tryptamine and secologanine, which is a monoterpene. So from strictozidine, there are several biosynthetic pathways that are possible, such as this one. But one of the main pathways is this one, the formation of gasoschizine. So you have a glucose here, a sugar. If you deglucosylate it, you remove the sugar, you liberated an aldehyde here that could condensate with this secondary amine. You form an iminium, which could be reduced here, and you get access to the tetracyclic structure of gasoschizine. From gasoschizine, there are several cyclization possible, and then skeletal rearrangement that can give you access to a lot of pentacyclic structure among the monoterpenoidal alkaloids. So I won't detail all of them. So from Gesso's, I will just talk about the pathway that can give you access to pleocarpamine from Gesso's. To go from Gesso's to pleocarpamine, you need to form a nitrogen-carbon bond between this formyl ester on the endolytic nitrogen, and you'll get to pleocarpamine. But there's also several other oxidative cyclization possible from the formyl ester. For example, the formyl ester could work at another position of the indole, at this C7 position, what we would call the C7 position, for strictamine. You can also react it with a C5 position to access to polyneuridine, or you can also make it react with this tertiary amine to access noracylcinidine. So in our case, what we wanted to do is again a bio-inspired synthesis of pleocarpamine, and to do take Gesso's and to form this N1C16 bond. So what is known in the literature, there's some work from Day-3 that demonstrated that it's possible to do an oxidative coupling between malonate, this dimethyl malonate, on what we will call the C7 position of the indole to form a carbon-carbon bond. Jepingzhu, when he wanted to do the same reaction from this substrate, he discovered that the same condition, LEH-MDS, then addition of iodine, didn't end up with the formation of the carbon-carbon bond, but of the formation of carbon-nitrogen bond, the reaction between the nitrogen of the indole and the carbon of the malonate. So how this reaction works? So first you have a strong base, LEH-MDS, you deprotonated the indole, the malonate, you form a bis anion, then you add an oxidant, probably to form a base radical. There's also a pathway possible, and you form either the carbon-nitrogen bond or the carbon-carbon bond. This reaction really depends, it's really substrate dependent. It depends on what is the substrate, your starting material. So our question was, what will happen for Gesso's? So first of all, we needed to have Gesso's in hand. So I won't detail this reaction, this scheme a lot. We just combined two known syntheses of Gesso's in the literature, the one from Steve Martin and the one from Jean Cook. So form a Villeneuve-Cook's manic reaction on the C-mean to form stereocenter at the C3 position. Then allylation with this allyl bromide. From this compound, we obtain this vanadium iodide, addition of nickel. Then we did a radioactive egg reaction with a nickel, not catalyst, but promoter to form this carbon-carbon bond. And then we needed 3 steps to remove the carboxylate here, the benzylic ester. And that formulations have to give us access to Gesso's. Then when you take Gesso's, treat that with KHMDS and KHMDS on the iodine. We didn't obtain strictamine or pleocarpamine as we expected, but we obtained the structure of noracylcinidine here. We did not have the formation of a carbon-nitrogen bond from pleocarpamine, of a carbon-carbon bond for strictamine, but formation of the C16 bond of the formyl ester on the N4 nitrogen of this tertiary amine. We probably, so this tertiary amine here is quite reactive nucleophilic. So it's possible that you form this iodoammonium, which would then react with NO8 that you will form from the formyl ester. And that's why we form this carbon-nitrogen bond. Then from this compound, just a saponification gave us access to the first total synthesis of noracylcinidine, which was still interesting to do. So to make the nitrogen of the indole on the C16 carbon to react, we had the idea to bring them close together by forming this chlorolactam. So the idea is to do a kind of Azar-Favorsky ring contraction by having the nitrogen of the indole to add to this carbon-chlorine bond to form this really reactive intermediate on which a methanol could add and open this oxoaziridinium ion and get access to chlorcarpamine. It was probably a little too naive, so it was not complicated to form this chlorolactam, 7-membrane chlorolactam from deforming gasoskizine. Unfortunately, when we had methanol, which concentrated the water with a base, we didn't obtain chlorcarpamine following the same that I showed you better, but we obtained again norexelcinidine, which makes sense because this tertiary N4 tertiary amine is much more nucleophilic than the indole nitrogen. So what happens is the N4 tertiary amine displaces the carbon chloride bond, and then methanol or water add to this amide to open the lactam, and you get to norexelcinidine. So how can we make this carbon nitrogen one of chlorcarpamine? One of the problems that we identified is that in gasoskizine, it's mainly trans conformation in which the N4 nitrogen and the C16 formylexer are really close together. That could explain why we found norexelcinidine. If you want to react this formylester with indole nucleus, either for strictamine, carbon-carbon bond, or chlorocarbamine, carbon-nitrogen bond, you need a cis conformation with inversion at the nitrogen, of the lone pair of the nitrogen. So how can you do that? Tanya Gash actually demonstrated that if you benzylated gasoskizine, you lock the cis conformation. And our idea is to take this ammonium, the same kind of ammonium that Tanya Gash synthesized, and do the oxidative cyclization on this substrate to try to obtain chlorcarpamine or maybe strictamine. So that's what we did. From deforming gasoskizine, actually, we didn't use gasoskizine itself, but this malonate derivative. Then we did the benzylation on the N4 tertiary amine. So this tertiary amine reacts with paramethoxybenzyl bromide. You form this ammonium and N4. So the nitrogen is not anymore nucleophilic or reactive. Only in addition, you have a cis conformation. Then we did the Mazu oxidative cyclization. You double deprotonation with KHMTS of the indole on the C16 malonate. Then you add the oxidant, iodine. And for the first time in our case, we are really happy to see the formation of the N1 C16 bond. So we had the skeleton of gasoskizine, so we can remove the paramethoxybenzyl with BBr3. So we restore the tertiary amine. So now we need to remove one ester to get to chlorcarpamine. So usually you do that by a Krebs-Shaw reaction. So we did a Krebs-Shaw reaction on this malonate. So decarboxylation, removing of one of the ester was possible. Unfortunately, we didn't obtain chlorcarpamine, but it's C16 epimer here. In fact, chlorcarpamine is like a cage, and in chlorcarpamine, the ester is inside the cage. And in epichlorcarpamine, the ester is outside the cage, which shows it's a more stable compound. So now what we are trying to do is convert epichlorcarpamine into chlorcarpamine. It's not so easy to do. I'll just show you that we can also make another natural product related to chlorcarpamine, is hydroxymethyl chlorcarpamine. As I told you, in this malonate, it's a cage. One of the ester is inside the cage, and the other ester is outside the cage. So you can reduce selectively the ester that is outside the cage into this aldehyde. This aldehyde, you can reduce it again with sodium borhydride into hydroxymethyl chlorcarpamine, which is a natural product. And when we add a base and we heat that, we can do a deformylation. But again, we didn't obtain chlorcarpamine, but epichlorcarpamine, which is a more stable compound. So going from epichlorcarpamine to from pleocarpamine to epipleocarpamine is still an ongoing task. We can do the total synthesis of another natural product, which is taberdivarine. Really interesting, this compound is a process an ammonium and 4-ammonium, and also the stereochemistry of epipleocarpamine. So it was a much easier compound to make, because you can take the malonate, methylated it with methyl iodine, you form this ammonium and methylammonium this time. You do the oxidative cyclization, you again form the N1-C16 bond. This time you don't need to remove the ammonium, because the ammonium, you find it in the natural product. And then you do a double saponification of the diester, followed by heating to do a decarboxylation, and we get taberdivarine H with this N-methyl ammonium in this carboxylate, which is a sweet ionic natural product. So to tell the truth, at the same time as we published this compound, the group of Takayama reported the first total synthesis of pleocarpamine as a minor, with a modest yield, and also to the epipleocarpamine. To do that, it did carbenoid insertion of a carbenoid into the N1 hydrogen bond of this compound. And as we did, it needs to log the cis conformation of Gelsowski gene. It did that by forming this amino bowing. And then from this compound, it was possible to him to form this nitrogen carbon bond from this diazo compound in presence of a rhodium catalyst. The main compound, after oxidation of the amino boron, can restore the tertiary amine. The major compound is the pleocarpamine, but he managed to obtain a little bit of pleocarpamine. As I said, this work from Takayama was about the same time as us. Do we have 5 more minutes or no? So yes, if
you can continue. You can continue 5 minutes.
Okay, I'll try to do it in 5 minutes. So so I don't talk anymore about pleocarpamide, but also another monoterpene indole alkaloid. I explained you before Gelsowski, the transformation of strictozidine of Gelsowski is one of the major pathways giving access to a lot of monoterpene indole alkaloid. But there's also a minor pathway from strictozidine. It's also possible to oxidize directly strictozidine into thymosin, for example, this natural product. So how you do go from strictozidine to thymosin? How you do transform this compound into this really complex cage structure? In fact, when you look at it, it's quite simple, because you can imagine oxidizing strictozidine into this hydroxyindolenine, and then the enol ether part of the monoterpene part, the one that comes from secologanine, could add to this imine at C2. You form a carbon-carbon bond, and then you add an oxocarbenium here, which is really reactive, and the oxygen at the C7 position of the hydroxyindolenine could intercept this oxocarbenium, and you form 2 bonds on the skeleton of thymosin. So that's what we wanted to do, actually. So it was easy for us to prepare strictozidine analog, which is this compound, which instead of the glucose here, we have ethyl ether. So like, as you say, it's the same compound as here. Instead of having the glucose part, we have a diethyl ether. So we prepared this secologanine starting material the same way it was described by Titzer 30 years ago. I go fast on that. Knoevenagel condensation to form this enal that can react in a heterodisalder manner. So from sulfoxy elimination, deprotection of the aldehyde. Then a Pictet-Spengler reaction with tryptamine give you access to this strictozidine precursor. Then from this compound, on our model substrate, such as this one that doesn't have the double bond here. So in this substrate, you don't have the double bond that you find here. So we try to oxidize with different oxidants this compound, but really a mess happened. We were not able to obtain the compound that we desire. But if you protect this nitrogen with a noisy group, and if you oxidize this compound with this oxaziridine, we are really happy to observe the formation of the pentacyclic of the 5-membrane furandoline part that we can find in thymosine. And you can also do the same reaction to the substrate that has the terminal alkene needed for the total synthesis of thymosine. So it works also here, and we obtain a quite good yield if you take into account that you start on a mixture of diastereoisomer here. So it's a 70% conversion of the good diastereoisomer. I'll explain a little bit some mechanistic stuff at the end. So we get this structure, the skeleton of thymosine. Then to get to the natural product, what we have to do is to introduce the sugar part, the glucose part of what that you can find in thymosine. To do that, we hydrolyzed this acetal to form an hemiacetal, acetic acid. So you replace the acetyl group by hydrogen, so you get hydroxyl group. Then you can do a glycosylation reaction. So here we have a racemic synthesis. The glucose part is almost enantiopure, so you can form the reaction of an enantiopure molecule on a racemic one. We gave you access to 2 diastereoisomers that you can separate. You can both engage this compound in the deprotection step, so you can remove the noisy group and you remove the 4-tetroacetyl. On one of the diastereoisomers, you can convert it to thymosine, and the other one you get a diastereoisomer of thymosine. So this reaction, this synthesis was really interesting because we have this really interesting oxidative cyclization. But one of the problems is that you start from that you obtain a racemic synthesis of the skeleton, and when you do the glucosylation, you lost half of your compound. So in order to improve the synthesis, you really need. It's better to start from a strictozidine compound that is enantiopure. For that, you need the synthesis of secologanine, which is enantiopure, and which was described last year by Ishikawa. So we just reproduced the work of Ishikawa to take protected secologanine in an enantiopure form. We did the Pictet-Spengler reaction and get 2 diastereoisomers that we don't separate, the one corresponding to strictozidine. We did the same oxidative cyclization as before, and after the protection, we get to thymosine. Interestingly, the other diastereoisomer, so epimer at this position, doesn't react with the enolator part, enolacer part, but react by this exocyclic double bond, and we get a really interesting structure. As I said, the mechanism is probably really similar as what happened in nature. First, you have the formation of hydroxyindolenine. The nosyl group is really important to sequester the activity of the N4 amine, but also to direct the oxidation of the indole, because the nosyl part probably lie under the indole on which directs the diastereoselective oxidation. Then once you get this compound, is the same as before. The enol part add to the imine, and then you have the oxocarbanion, which will be intercepted by the oxygen, and you'll form the polycyclic structure of thymosine. If you have the other diastereoisomer, the enolator cannot add to this iminium. Therefore, it is 18C19 exocyclic alkene, terminal alkene, that will add to the C2 position of the hydroxyindolenine, and then you have a similar reactivity, which explains the formation of this other compound. So now I am finished. I would like to thank all the funding agencies, the people that work on this project. So you could see the name of all the people that work on it. I would like to thank in particular Dr. Raj Kumar Nandi, that was a 2 years postdoc in our group, who did a lot of work on the iron chlorine chemistry. So I would like next to thank you all for your attention. Thank you very much.
Okay.
So yeah,
I think I'm audible. Thank you, Guillaume, for your wonderful presentation on the de-aromatization of indole using the ITC Fe catalyst and tephlic acid, as well as the electrosynthesis approach, as well as the application of the total synthesis of the 16-Fe, thiocarpamine, as well as the different type of the complex natural products. So we have a shortage of time. We can take few of questions. It's okay, no problem. So one of the participants would like to ask you which synthesized derivatives are application-wise most significant.
Sorry, which is most significant?
Synthesized, yeah, most significant in terms of the application.
It depends on the point of view. If you want total synthesis of natural product, the one that gives you access to bipropylene, I think for us, for natural product chemistry, it's really interesting, the more interesting. But so go to that, sorry. It depends your point of view. I think this reaction is really beautiful, that this one here, because it can give you access to this really complex natural products. But if you, I think in the drug discovery point of view, working to discover new drugs, I think this kind of reaction of spirocyclic spiroindolate with stereomethyl group could be a really nice way to prepare a drug-like compound. It depends what we want to do. It depends your point of view.
Oh, okay. So I can take one more question. There are a few questions in the chat box. So this is the last one because we have running behind the time. Why hydroalylation is so selective in N-acyl indole, and what about N-BOC and other electron withdrawing on the nitrogen?
So we tried several other group on the nitrogen. The BOC with iron chloride doesn't resist the condition. It just on the indole you get deprotoxin and then we get oxidized. So yes, we try benzoyl group. It works also, but the yield is lower. We really need acid group. We don't understand it really well, but it's really the best substrate, the best activity.
Okay, Dr. Guillaume Bhansali, for your very nice presentation on the total synthesis of the different type of the complex molecule indole base using the de-aromatization. On behalf of the organizing committee, we convey very thanks to you. I hope we can visit again personally if you sometime come in the India.
Yes.
So we can visit in our university. Okay. Thank you very much, Guillaume.
Thanks very much.
Okay. Thank you.
Bye.
So with this, just a minute. I think Professor Debabhrata Maiti already joined in our group.
Yes, I am here, Raj.
Okay. Okay. So we can go in the final lecture.
Can you see me and can you see my slides as well?
Yeah, I can see you and your voice is audible.
Okay, fantastic.
Fine.
Thank you.
So we almost come to the end of our webinar series. The last lecture of the day 3 as well as the last lecture of this webinar series of the International Virtual Symposium on Advances in Chemical Science. We are very lucky and very happy also. We have with us Dr. Debabhrata Maiti, who is an associate professor of Indian Institute of Technology, Mumbai, who did his PhD under the supervision of the Carlin in the MIT in the John Hopkins MIT, and then he did his postdoctoral with the book world. And then 2008, he joined the Department of the Inorganic Chemistry at IIT. And currently he is an associate professor. His research interests are focused on the development of the new and sustainable synthesis of catalytic methods. He is associated in various editorial boards. He is an associate editor in the Journal of Organic Chemistry. Very recently, he received the Fellow of Royal Society Chemistry Award. Is a member of the editorial board of Chemistry European Journal, as well as the editorial advisory board of the Organometallics and Asian Chemical Journals, and very reputed international journals. With this short introduction, I would like to invite Dr. Debobroto Maiti to present your lecture. Thank you.
Thank you, Raj. Hello, everyone. It's a pleasure to be here and to share with some of the ongoing research work with all of you here today. Raj, I know him for quite long now. He's one of our family member and as well as close family friend. So, it gives me a great pleasure to be associated with him and to talk here today. I wish I could have visited all of you in person. I'm sure that opportunity will come many more time in future. I wish you in advance, happy Durga Puja. I hope all of you are keeping well in this extremely difficult time. Let us try to look at what we are trying to do in our laboratory at IIT Bombay. Well, of course, over the last 6 months, we are completely shut down, just like almost many other places in India. So this work is mainly, the work has been done recently before the pandemic started. We are focusing on developing carbon-hydrogen bond functionalization reaction. I think one of the biggest challenge our society faces today is to provide simple solutions for complex problems. And this is pretty much something we are trying to achieve in our laboratory. For inspiration, we look at nature. As all of you know, biological transformations are extremely efficient and highly selective. Here is an example of a biological transformation, a very useful enzyme, cytochrome P450. It's a metalloenzyme. It has a active site where you have porphyrin iron center. But most importantly for us, the organic molecule that is involved in this reaction is really appended very close to this active site. So if you look at this huge organic molecule and this metal center, this organic molecule has many different carbon-hydrogen bonds throughout the molecule. But selectively, due to its orientation, you see only one carbon-hydrogen bond is getting functionalized. Nothing happens to these other carbon-hydrogen centers. Now, something like this, some reactions like this, where you have possibility of many things and selectively only one thing is happening, is quite difficult to achieve in synthetic setup. Well, that is where particularly we are trying to see if we can devise strategies which can mimic enzymes and will be able to deliver excellent synthetic transformation. You can look at many other organic substrates, such as, let's say, one in here, which is in cartoon form. In this organic molecule, you will find many different carbon-hydrogen bonds, as I have depicted over here. But the challenge is, can we selectively functionalize, let's say, for example, this position precisely, or this carbon-hydrogen bond precisely? Do we have synthetic strategies so far in our hand that can allow such transformation? A simple answer to this question is not really. We may be able to control this functionalization at this proximal position, such as this alpha position or beta position, to a greater level of selectivity and greater level of efficiency. But the moment when we want to promote a functionalization at, say, for example, a gamma position or a delta position or as an epsilon position, these transformations are not feasible. Essentially, you don't get any product. not only the selectivity is the issue, the product formation never really happens if you are really looking for the functionalization at a distal position. For example, I'll give you a simple example. If you have, let's say, decane, now at the 7th carbon of decane or 6th carbon of decane, can you do the functionalization or any reaction selectively? These are extremely challenging transformation. Some strategy need to be developed if we are to think of promoting these reactions efficiently. Let's try to see what has been done a little bit so far in the literature and what presumably we are trying to achieve in our laboratory. Here is a series of compounds all of you are familiar with. These are amino acids, right? It's a very important entity both in synthetic chemistry, in biological system as well. But if we are to answer whether this gamma position, which is highlighted over here, can be selectively reacted to produce different other amino acid derivative, which could be useful, let's say, for example, as a pharmaceutical or in material science or many other research activities as a building blocks. The answer, once again, is not really simple. We could not promote a selective reaction at this CH bond because there are alpha, beta, and other positions such as delta and other positions also available in these molecules. Now, this is where we started thinking. Of course, there are quite a lot of exploration done in this overall domain, but the selective functionalization at distal positions, such as, let's say, this gamma position, remain still challenging. Okay? We started thinking, can we utilize this molecule itself to promote this functionalization at this position? In other words, if we take a metal complex along with this, can the metal bind with this ligand? Because this is a good ligand or decent ligand. This is also a ligand, right? Can a metal bind with this center and activate this carbon-hydrogen bond? Well, we tried to do that. Despite our best effort, we could not promote any reaction which can selectively functionalize these positions. So no matter what metal or what sort of strategy we adopt, these positions could not be functionalized easily. And also in the literature, there is no example. So this is where we thought that perhaps we can introduce a good ligand, because this is a ligand, like carboxylic acid, as you know, it's a ligand for metal center, but it's not an excellent ligand. At best, it's a monodentate ligand or little bit more than perhaps monodentate ligand. Since the metal coordination is not that very strong, and perhaps that's why this is not able to promote the selective functionalization or any functionalization efficiently. We thought that we will introduce a good ligand, such as that is in here. This is a bidentate ligand. As you can see, this is 8-amino-quinoline. This is quinoline unit, 8-amino-quinoline. You can attach 8-amino-quinoline over there. Once we have done that, then we see that with, of course, in this case, palladium as the metal, we can activate this position. That means this CH bond selectively. The other carbon-hydrogen bond that is over here or there remained unactivated. Of course, the formation of a preferable ring formation as well as the suitable steric demand has promoted this intermediate, but nonetheless, it was found that once we have introduced such a ligand, such as 8-amino-quinoline, we can selectively activate and metallate this position. So perhaps I did not mention, our group is mainly focused on organometallic chemistry and subsequent synthetic transformation. So all the transformation I will be talking about will be metal mediated. Now, with this strategy, then we are able to show that many reactions can be selectively promoted at this position. Once again, no other positions are getting affected by these transformations or by this strategy. If you now look at a series of different functionalization, maybe carbon-carbon bond formation, carbon-selenium bond formation, carbon-sulfur bond formation, carbon-germanium bond formation, carbon-silicon bond formation, all these many different functionalizations. Of course, there are many more also we have been able to promote. All these transformations can now be promoted by this simple strategy. Quite interestingly, we see that the diastereoselectivity for these reactions can be quite high. Of course, 50 to 1, I would say it's really, really satisfying. But these are the best ones. Of course, there are not so good ones. But nonetheless, in the important compound, we can also go up to 25 to 1 or 19 to 1, 18 to 1. That makes an feeling or gives us a feeling that these transformations are quite efficient and selective, and we can promote these transformations very precisely at a desired position. Of course, you may be wondering, are these the only amino acid? Of course, there are many other amino acids, such as, for example, leucine. Leucine has alpha, beta, gamma, as well as delta CH bond. Can there be a strategy where selectively this delta carbon hydrogen bond can be functionalized without affecting the alpha, beta, or gamma CH bond? Once again, we have tried to do this reaction without introducing any ligand, any further Hello, Raj. Hello, Raj. Anyone here?
This is Pujarini. Sir, you can please continue. I think Dr. Nandi has not been able to log in. There was some power issues there.
Yeah, well, over here also I have, all of a sudden it never happens really.
Yes, sir. You can
Internet
just
outage.
continue, sir. Yeah, yeah.
Okay, sorry for that. Sorry, everyone.
No issues, sir. Yeah.
Yeah, okay, so yeah, I was here. I hope I still have some audience left, right?
Yes, sir. There are over 80 people
Hello.
watching.
All right, all
Hello.
right. Okay, hello. Yes, I can.
Dr. Nandi is back.
Am I audible?
Yes, you are. I'm glad that I'm also back. It never happens usually in IIT that we lose internet connection, especially in weekdays. It never happens. Almost
So it
never.
was from your side or my side? I thought it's from my side because power cut is gone. There was some power cut in my place. So
No, I think there was a connection problem at the other end as well, Dr. Nandi.
okay.
Yes.
Okay.
So
we can
just continue. Yes.
Dr. Maiti. Hello. Dr. Maiti? Hello.
Dr. Maiti's video is paused. I think
Yeah.
connection issue there. Dr. Nandi, am I audible to you?
You're audible.
Okay, I think it has, the connection has gone from the
From the
speaker's end. Yeah, we'll have to wait for sir.
We can wait for a few moments.
Yes. Let's wait for sir to log back. Yes.
Happening.
Yeah, now it's fine.
Now
I can
fine.
see your video.
Yeah. Okay. Okay. I don't know what to do.
Now
if
it's working. You can continue. It's fine.
All right, so let me get back to our work then very quickly. So, as I was trying to tell you that if you have a suitable metal cycle formation, it is possible to almost do any reaction, almost anything you can name it in the textbook or anywhere you have seen, any reaction, irrespective of the nature of the reaction, you would be able to do this reaction at this ortho position. But that, of course, brings the question, can we design strategies which will be able to bring the metal at the meta position? If you look at, let's say, our bachelor level of studies, there are many reactions that can selectively done at ortho position, but not can be done at meta position, or vice versa. But can we do any reaction, be it, let's say, nitration or even alkylation, acylation, at, let's say, for example, this meta position? Any reaction irrespective of the electrophile or nucleophile, if we are able to introduce the metal precisely and design the strategy correct, perhaps we can then be able to do such reaction. What it turned out that it requires to design this template a little bit efficiently, because no matter what we do, this ortho CH functionalization is always predominant, because this is thermodynamically and kinetically preferred product formation pathway. If you are to promote a distal, this meta CH functionalization, you have to essentially outweigh the preference for this ortho CH functionalization. I will not take you to the details too much, but what we were able to show that if we are introducing the simple ligand, of course, the substrate itself that is in, let's say, black here, cannot promote this reaction at the distal position. But substrate itself may be able to promote this reaction at the ortho position. You need another ligand. So the one you see in the brown color is the ligand. Now this ligand will hold to the metal with this heteroatom over here, for example, and then selectively will be able to activate this meta position. As you can see, with these strategies or with this simple cyanophenol or cyanobenzoic acid, depending on the organic substrate that you have, you can introduce the functionalization selectively at the meta position. These reactions, a series of these reactions were not really ever possible before to do selectively at this position. Okay, so with this cyanophenol or cyanobenzoic acid or suitable variant of it that has been shown previously in the literature, it is now possible to do a series of functionalization with various organic substrate. As you see that this is one of the organic substrate. Each of these are different organic substrate that is in black here that can be selectively functionalized. Various functionalization can be done. We have studied the reaction mechanism in greater detail. What it requires that the cyanophenol is attached with the organic substrate that is in black over here. Cyanophenol is the ligand or the directing group, whatever you want to call it. It attaches with this organic substrate, and the overall disposition is such that now selectively only this meta CH bond is getting exposed in front of this metal center. This ortho CH bond or para CH bond or any other bond that is present into the arene will not be really interacting with the metal center. This overall orientation helps it to activate this position. Once you are able to metallate it, so this is the organometallic intermediate formation, we then be able to form these reactions selectively at this position. Of course, we try to do the reaction mechanism or understand the reaction mechanism in greater detail, both in terms of experimental studies as well as the computational studies. And we find that such a mechanism is perhaps occurring in these cases. Of course, detailed mechanism is a little bit more complex than this, but this is a simpler version of the reaction mechanism that we can put forward. Well, then, of course, the next question comes, is it going to be really useful for every kind of reaction at this meta position of this arene? Or is there many limitations? How about the selectivity issues? Is there no product formation at this position or very little? Well, often we see that very little other product formation, but
Hello. Am I audible? Hello.
Dr. Nandi, I think there is a problem with the speaker side, the internet connection.
Okay, okay.
Yes, we have to wait
we
for
can
some.
wait for
Yes,
a few more.
yes, yes, yes.
Yeah, Dr. Maith is back. Can you unmute yourself, Dr.
yeah,
Maith?
yes, I am. It's quite a eventful day, looks like. Okay, I hope you can be with me. Sorry for all this trouble, which I have no control on.
No, it's fine. It's technical issue. It's fine.
Yes.
And take your time.
Okay, can you? Yeah, yes, I am. It's quite a eventful day, looks like. Well, I don't know why I'm hearing again myself.
Can you mute your YouTube? I think you.
I see.
Yeah.
Now,
Just close you.
Can you see me now?
Yeah, I can see.
And the slides are back?
Yeah, he's back.
Okay, all right.
You can continue.
Yeah, I hope it lasts a little longer for me to finish it. Let's see. So the type of challenges that we are facing are very simply that the metal positioning is not really perfected. So metal is traveling between this side as well as that side. If that happens, as in the last slide you see, if sometime metal is over here or over here, the positioning of the metal will dictate which carbon-hydrogen bond is getting activated, right? And that would mean the selectivity and of course the yield of the desired product would be probably.
Now he's back. I think there is some problem with Professor Maiti. Can you unmute yourself, Dr. Maiti?
I
Yeah,
am.
it's fine.
Okay,
Mr. Rajesh is fine.
Yeah, okay. Sorry, Rajesh. Okay, let's get going once again. So this is where we thought that we'll have this further stronger coordination. Okay, I'm gone back or I'm still here.
Just share your screen, please.
Yeah, so with this, now we thought that we'll have little bit better coordination and that is, we will have a little bit strong.
Dr. Maiti, just a minute, I'm interrupting you. We can't see your screen. Can you share your slide, please?
Okay.
It's perfect.
Okay. Now that's why we thought that we'll have a better ligand than the nitrile. So we started walking away from nitrile and have introduced this 8-methoxyquinoline, and finally when we arrived at 8-nitroquinoline, we see that this reaction now can be done selectively still at the meta position, but it can be done at room temperature. Both the yield and selectivity can be further improved than what we were seeing in cyanophenol. But as you would have noticed, previously it was a very little ligand, such as cyanophenol. Now this brown color ligand is really gigantic. That means that we are going to be more expensive in the process if we want to really make this method commercial or make this ligand or system commercial. It is going to cost much more to the user. This is where we again went back to the chalkboard. We started thinking, can we overcome the limitation of the nitrile in a little bit more convenient way than that we have done already? So by thinking towards this, subsequently we have started wondering and designing this ligand. And when we arrived at this biphenyl pyrimidine-based ligand, we find that this is really, really suitable or more useful than what we have seen so far. In a way, this pyrimidine-based ligand system is a better ligand for the metal center. In other words, this is a better sigma donor as well as pi acceptor, which is essential for holding onto the metal center more efficiently. Something similar argument you may have seen in case of metal carbonyl complex, for which carbonyl species and metal carbonyl compounds are becoming a little bit more stable than they are usually can be expected. And therefore, what we find that compared to cyanophenols, this new generation, or we call it the, at least the second generation of this template that we designed, is becoming much more effective than the first generation template that you have seen previously in the cyanophenol cases. With this good ligand, we see that now a number of reactions which were previously unsuccessful or not really feasible to promote, now we are able to promote quite efficiently. In addition to this, we of course have this Thorpe-Ingold effect. That means the substrate and the ligands are coming closer with respect to each other, and that is pushing this efficient functionalization. We have two different heteroatoms. That means that one of the heteroatom will be coordinating with the solvent, usually hexafluoroisopropanol, quite expensive solvent if you may think, but it is the good solvent that works for this reaction. All these efforts put together, as you see in this highlighted section, there are many combinations of the approach or the designing aspect with or without understanding. Let's say at the beginning, we were able to promote this functionalization in quite high yield and great efficiency. By now, we understand the effect of each of these components, both by experimental studies as well as computational studies. But more importantly for us, what we are able to show that previously with the cyanophenol, these alkylase and cyanation reactions were not feasible at all. Now we are able to promote these reactions quite efficiently. In the process, also we realized that this ligand that you see in the brown over here is quite a good ligand compared to the previous generation of ligand. That means this CH bond activation step in case of cyanophenol or cyanodirecting processes often are the rate limiting step, but this ligand allows this CH activation step to be even non-rate limiting. It's becoming an easier step compared to the cyanophenol ligand. So the benefit of a good ligand is essentially promoting a certain stage much more efficiently than that was possible with a not so good ligand. So with this good ligand, this step becomes non-rate determining and reversible, and now we can even introduce the deuterium labeling. If we want, let's say with the deuterated acetic acid, we can deuterate this position. And also it allows many other transformations. For instance, this is one of the cases where we are really excited, and that is precisely because of the fact that how far this transformation can be extended. Let's say if you have an arene, can we have the meta-CH functionalization of arene irrespective of the nature of the arene or the substituent that is present in the molecule? Well, as it turned out, we can keep on increasing the linker length between the arene and template, but the metal center that is bound with the template, this let's say nitrogen atom, it will bring the metal precisely to the meta position without touching too much of the ortho or other position in the arene molecule. We can keep on increasing the length and the type of substituent that might be having in the linker length or in the linker, still it is meta substitution or meta functionalization. So it increasingly looking like almost every organic molecule perhaps will be able to undergo meta-CH functionalization as long as you are introducing this sort of ligand with the organic substrate. Of course, that's the limitation. One limitation is you have to introduce the ligand and then you have to remove the ligand. But since there is no other approach or no other reliable approach exists, perhaps this approach can be quite efficient in or quite useful, I would say, in promoting these reactions selectively and precisely at the meta-CH position. This is another reaction with this ligand. Of course, this is a very challenging reaction, I would say, in the context of not only CH functionalization, in the context of any reaction. You can look at, let's say, even the Heck reaction. These substrates are quite challenging, internal olefin substrates. Now, with this improved ligand or the next generation ligand, what we are able to show that even the internal olefin can be introduced to give this interesting allylation products in these cases. I'll be little quick here. Also, with this ligand, we are able to promote this alkynylation reaction, another interesting reaction, so-called inverse Sonagashira type of reaction. Selectively at the meta position, it was possible to promote. We can synthesize a number of drug pharmacophore conjugates. By utilizing this method, we understand the mechanism of this reaction in greater detail. Not only these exciting transformation, even the allylation, let's say so-called Suji-Trost type of allylation reaction, selectively at the meta position, at the expense of carbon-hydrogen bond, no carbon halide bond is required. Selectively and efficiently, this transformation can be promoted at the meta position to give this exciting meta allylation product. Either it is terminal or even the internal allyl product can be generated. Both the yields and selectivity can be synthetically useful. And therefore, I hope so far I'm able to tell you that it is now possible, in addition to the ortho-CH functionalization, designing of the template so that template will dictate the metal coordination and displace the metal in such a way so that selective meta-CH bond of an arene can be possible. Now, what about then one more step further to promote the distal para-CH functionalization? For distal para-CH functionalization, there was no reliable approach wherein by designing the template, one can reach the para position selectively. As you can see, it would require a huge transition state formation as a design of the template. And of course, we have to override the formation of the metal complex at this position as well as that position. So we have to prevent the functionalization at these two positions effectively in order to promote this reaction quite efficiently, selectively at the para position. What we essentially realized after much experimentation and many attempts and failures, I would say much more failure than any success that we got, we realized that this biphenyl scaffold is going to be essential for promoting these transformations. With this biphenyl scaffold as a part of the directing group, we now find that with other components placed in perfect or designed perfectly to bring these moiety together and placing the nitrile moiety at the ortho position as it's shown in here, not in any other position. This phenyl ring has to be over there. If every aspect of this transformation is or of this design is perfected, then we are able to selectively deliver the metal to the close vicinity of the para position. So this was the first example in the literature to show that the delivery of the metal is even possible selectively at the para position. This is a product crystal structure which clearly shows that how the putative transition state would look like where metal is getting delivered at the para position. So this is why we call it a D-shape template. Once again, as you can see, the yield as well as selectivity is synthetically useful for such distal CH functionalization reaction. Well, one of the things that we realize in the process that very simply the design of this directing template, which is brown in here, has to be really perfected. There is very little margin of error, so to speak, in terms of design, because if any positioning change of the nitrile or any positioning change of this phenyl or any of these aspects, if you change, both the yield as well as selectivity will be completely missing. Well, therefore, we thought that we'll try to modify both the electronic nature of this bottom phenyl ring, because the top phenyl ring changing too much was really detrimental. we find that when we introduce this dimethoxy group, there we can introduce this hydrogen bonding, which essentially helps rigidifying this overall orientation and brings the metal to the close vicinity of this para position, and therefore selective functionalization at the para position becomes much more facile. This is why we called it as a second generation template, where these two dimethoxy groups are there, and we see much improved yield and selectivity and newer functionalization that was not happening without the dimethoxy group. Now with this dimethoxy group, it was possible to promote. For instance, with this modified directing group, now we are able to promote the silylation reaction with acceptable yield and as well as selectivity. Here is the reaction mechanism, which you may have presumed by now, that the metal center will be held by the ligand, and the organic substrate will be displaced or positioned in such a way so that para-CH bond only, not ortho-CH bond, not meta-CH bond. This precise design will allow the activation of the para-CH bond precisely, and the metallation at this position and subsequent organometallic transformation would lead to the product formation. So Raj, I can have 10 minutes extra, I believe.
Sure, you can continue,
Okay.
No problem.
Thank you. So what we are able to then show that with the designing of the template, we can really able to dictate or control the metal positioning. As long as we are able to position the metal really more perfectly, we can control the functionalization at that particular position, right? Now, one of the questions that you may be thinking, whether palladium is the only metal that is working. Well, many other transition metal we have tried. What we essentially see that this ligand system is not really that great for anything but palladium. Very recently, we see that we can introduce rhodium for such distal meta or para-CH functionalization reaction with this sort of ligand. Well, to summarize this part, I hope I'm able to briefly tell you that if you have an organic molecule like this, and you want to introduce a ligand, this ligand can be any of these. If you are introducing the cyanophenol-based ligand, this is one of the ligand that is now commercially available, you can promote the meta-CH functionalization. As I was trying to tell you that this is the best ligand so far for the meta-CH functionalization reaction, and it really works better than anything else that is out there. In terms of the para-CH functionalization, these are the first generation template that we wish to introduce with the organic substrate for the para-CH bond activation. These are the second generation template where we have the dimethoxy substituent for the selective para-CH functionalization. Well, therefore, I am sure you must be wondering that this is not going to be a great method, not really ideal method, at least for the synthetic chemistry, where the ligand need to be attached with the organic substrate, do the reaction, and then removed during the process. And this is where, of course, the community as such, all of us are trying to see how to overcome this limitation. One of the strategies that we are trying to promote at this point is the in situ bond formation and removal, rather than a direct covalent bond formation and then doing the reaction and then removal. So if we can have in situ bond formation, which attaches the organic substrate as well as the ligand during the reaction, and then we are able to promote the reaction and cleave it during the reaction, so the further hassle of introducing and removing perhaps can be overcome. So therefore, the three steps perhaps can be cut down into one step or one pot reaction perhaps could be possible. And this is where we thought that we might rely first on the imine-based complex, where you take aldehyde or amine as a substrate, and the counterpart will be forming with respect to the ligand, where these in situ formation and breaking might be feasible. Well, such a strategy already exists for the ortho-CH functionalization or the proximal sp3 carbon hydrogen bond functionalization. But for the distal CH functionalization, this is quite a challenge. And that is mainly because the moment you are trying to introduce the metal with the directing group, in presence of an imine, this imine nitrogen will hold to the metal center, will precisely, almost 100% precision wise, it would promote this functionalization at the ortho position. Almost there is no way one can think of promoting the metal precisely with the directing group, which is here, let's say those directing group that we are designing, but this imine nitrogen is not binding with the metal center. This is such a trouble that despite many attempts or many design, we completely fail. Of course, in the literature, there exists no report so far which can promote this functionalization with respect to the imine coordination or imine designed directing group. So we invested quite a lot in terms of designing. Finally, we arrived at this biphenyl scaffold with the biphenyl pyrimidine directing group. And then we see that this sort of transformation can be feasible. What we then essentially find is we do have this biphenyl aldehyde as a substrate and this biphenyl amine that is such as, let's say, this one, which is the best one so far. We have tried a variety of ligand that you would imagine, that type of ligand that we were discussing for the covalent bonding, that sort of ligand, many different designing aspects we have tried to promote. And we now see that this sort of transformation is possible if we have a suitable biphenyl pyrimidine ligand-based system. With this ligand and with this substrate, so this is the aldehyde organic substrate. If we introduce this ligand, now in situ imine formation and olefination, for example, or the metafunctionalization with respect to this bond can be possible with good yield and selectivity. This ortho-CH bond functionalization is not really happening too much. As you can see over here, so this aldehyde, biphenyl aldehyde, and this biphenyl amine with the orthofluoro substituent over here, with further tuning, we find that these two combinations will be able to form this orientation where this or the meta-CH functionalization will now be feasible. For example, various olefination reactions can be promoted, and these yield and selectivity once again can be useful. Not only aldehyde and amine, you can think of amine and aldehyde. So amine as substrate over here and aldehyde as substrate over there, or aldehyde as a ligand component over there. In situ, aldehyde amine forming an imine, and then this nitrogen holding the metal center to activate this CH bond precisely. And the imine nitrogen is not really activating this position efficiently, or not really at all in most of the cases, to give this functionalization in a desirable extent. So this is my final slide. Thank you all for staying with me. I hope I'm able to briefly tell you in the first part where the designing of the directing group, either you attach with the organic substrate, or even in few cases where you see the carboxylic acids can be directing the distal CH functionalization, it is possible to promote some distal CH functionalization at a desired position or at some desired position selectively. These positions are precisely distal position, not the proximal, so-called alpha beta position or the ortho CH functionalization. So this proximal CH functionalization, although remains many different problems still in the field, but we are hoping collectively we will be able to promote this functionalization, it better yield, better efficiency, and a variety of functionalization in this sort of aliphatic substrate. As you have seen with the meta-directing group, we can activate the meta-CH bond. This meta-directing group can be simple cyanophenol or cyanobenzoic acid, but you need to attach it, do the reaction, and then detach it. Well, for these cases, as you also see, the best one is the biphenyl pyrimidine-based ligand system. The pyrimidine scaffold will hold on to the metal and will activate the meta-CH bond precisely without attaching with respect to the ortho position or the para position. Selectively, only meta-CH bond is going to be activated. But more importantly, I think this sort of strategy is a little bit different. That is what we see in the textbook of, let's say, undergraduate studies, in our bachelor studies, where we see that in an arene at the meta position, let's say a particular type of reaction, either let's say electrophilic aromatic substitution or nucleophilic type of substitution, depending on the ortho, meta or para position we can promote. Now this is kind of overriding those preference, if you may say so, that in a given organic molecule or aromatic ring, irrespective of the ortho, meta or para position, electrophilic or nucleophilic substitution or any type of substitution with the help of organometallic intermediate, it would be possible. Same goes on true for the para position. We can promote this reaction with the help of the directing group metallation at this position, and irrespective of the type of reaction, whether it is a formally electrophilic reaction or a nucleophilic reaction, selectively we can do this reaction irrespective of what we have studied so far in the textbook, that this certain type of reaction cannot be promoted at the particular position such as para position or meta position. As you have seen, the limitation, as I was trying to also emphasize again and again, that you have to introduce the directing group and remove the directing group. Efforts overall in the literature by many research groups is ongoing, which shows that this is a strategy, another strategy which I did not discuss, that different strategy perhaps would be make one day feasible to promote this reaction selectively and efficiently without perhaps much effort. That means introducing and in removal of the directing group might not be necessary, but for that a number of things has to work out in future. With this, I think the most important slide is here. None of this work that I have discussed would be possible without very active and enthusiastic support from my students and collaborators, and of course the funding agencies for their support, continuous support. At this point, I would like to stop here and once again thank Raj and his colleagues for giving me this opportunity and having me here along with all of you today. And I'll be happy to have any question if time permits. Thank you, Raj, once again. Have a nice day.
Thank you, Dr. Marty, for your wonderful work, and your excellent work is presented by excellent way. In fact, these comments is done one of our research persons from Professor Ashok Mollik from Jadavpur University. I like your lecture very much, and we can take a few of questions from the chat box because due to shortage of the time.
Sure.
So there are many comments in the chat box. You can see it. So
thank you,
there
Professor.
is one question. Excellent work being presented is excellent way by Professor Mollik, and the question is from Nilotpal Sinha: can intramolecular cyclization of olefin be possible using distal functionalization concept?
Yes, certainly. I mean, that's an interesting question to think of. Of course, intramolecular cyclization is also possible, but only thing perhaps at the beginning we have to keep in mind the ring strain, if anything that is arising, how much ring strain that would cause. Otherwise, it is definitely one of the exciting pathway. This is indeed part of one of our ongoing project proposal, that where we are designing intramolecular functionalization, including the olefination reactions. Yes, that's it. Once again, that's a very good question.
Another question from Premananda Ghosh. So in the slide number 7, using melamine as a reactant in spite of 7-member lactone, it is expected to be a spirotype compound. Any special reason for this unexpected product?
That I think this is the precise one, I believe. 4, 5, 6, 7. This is precisely dominated by mainly the approach, and we believe we are doing the mainly we believe that steric bias at this alpha position with respect to this position is controlling the fact, and overall the transition state we are trying to see it computationally. We could not really answer by our modeling that very precisely, but computationally what we are started seeing that the reactivity barrier or the energy barrier between the spiro compound formation and this one is quite I think significant in the range of something like 10 kcal so far that we have seen. Of course, detailed studies, complete study is not really done. That perhaps is the reason why this sort of unusual mode of activation or bond formation is possible in this particular case. So the reason is not 100% clear to us, but we believe that we have some sort of idea at this point.
Okay. So another question is that for the last imine functionalization, why metal is not coordinating to the imine nitrogen and rather to be lower nucleophilic pyridine ring nitrogen?
Yeah, well, this is
about basicity.
Yes. This is really also another exciting question. I think we essentially, by designing the ligand in a way, so if you see the metallation at this position, okay, versus the metallation at this position, metallation of this position is I would say little bit sterically demanding. This just little bit sterically demanding over here, because this is ortho-substituted substituent we have over here. Over here, if you are looking at, or over here, if you are looking at, any of these pyrimidine one are not really having any ortho-substituent that the imine has to undergo over here. So this very subtle difference perhaps making us go for it. Okay, if you look at, I would not say that, unless you have really the design perfected, you would not be able to see this effect very precisely. You see, in every other cases, we don't have really that great of a yield or selectivity. Okay, now perfectly when we arrive on this is a better ligand. Okay, that is what I was trying to tell in some other slide in the middle of the talk, where this biphenyl pyrimidine or the pyrimidine is really a good ligand. Okay, that is because pyrimidine is in a way electron deficient compared to all these other ligands that you see over here. And the nitrogen, of course, nitrogen lone pair is not conjugated in these cases, pyrimidine cases. So it's a sigma donor, as well as being it electron deficient, it is also a decent pi acceptor. It's not a great pi acceptor, but a decent one. So the metallation at this position is feasible in part, of course, the steric region, as I was trying to say, also because of the fact that this is becoming a, I would not say an excellent ligand, but a suitable one, good one, relatively good one compared to, let's say, what imine has to offer, right? And this relative, affection or binding or stronger binding or relatively stronger binding, perhaps, shifting the balance towards the biphenyl pyrimidine or pyrimidine nitrogen coordination rather than the imine coordination.
Okay, so I think with this few discussion of the chat box, we'd like to thank to the Dr. Day-3 Maiti for your excellent presentation on the CH activation digital in the mode of the digital. I think our students and many of the participants have learned many things from your talk. And on behalf of the organizing committee, I would like to convey our gratitude and thankful to you for your presentation. Thank you, Dr. Maiti.
Thank you, Raj. Thank you all.
Yeah, if you have some time, can you stay with us for a few moments? We'd like to take some snapshot during the valedictory session. Thank you.
Sure.
Okay, so now we'll move to the valedictory session. To conduct this session, I would like to ask one of our co-convener, Dr. Pujarini Banerjee. Dr. Banerjee.
Thank you, Dr. Nandi. So we now enter into the valedictory session, the last of our sessions in this 3-day webinar series. So we would like to thank all the speakers who have been present here for the day. Thank you, Dr. Maiti. And to begin with the valedictory session, let me please invite Mr. Rajesh Parishad from the Royal Society of Chemistry. As all of you know, we have been associating with the Royal Society of Chemistry for this webinar. So thank you, Mr. Parishad, and it's over to you now.
Thank you, Pujarini. Thank you, Raj. I think at the outset, I would like to commend Dr. Raj Nandi as well as Pujarini and the faculty at the Diamond Harbour University to organize this fantastic webinar series. I understand it is quite a challenge to organize certain thing, such a scientific event in this COVID times. And I'm very impressed with the lineup of speakers, including a fantastic talk from Day-3 Mighty to conclude that. A big round of applause for the faculty of Diamond Harbour University. And I think RSC has been we are very keen to promote chemical sciences. I think we have been in India for the last 10 years as an office, and we have constantly like to work with the community in terms of promoting chemical sciences. And when Raj Nandi approached us to be part of this program, I think we were quite excited, knowing it's a women's university. I think we didn't realize that it was a women's university until we started speaking. I think RSC globally has been committed to a lot of the gender diversity issues. I think we came out with a couple of large reports which focused on diversity and inclusion. In fact, one of our earlier reports was on breaking the barriers, which really gave the gender perspective in terms of how women's chemists and what are the challenges faced by them as well. And going forward, I think we have recently come with the diversity and inclusion committee and a report which kind of looks at a broader aspects about these gender diversity, other inclusions. And we have been pioneer and forefront in this one, driving these initiatives, and very, very keen to look at that gender diversity aspects in India as well going forward. I think we would like to build a kind of a report in terms of how gender diversity, especially in chemical sciences in India, it would be a good platform to really interact with the Diamond Harbour University to understand their challenges in terms of how gender is playing a role in chemical sciences as well. Coming to the event here, I think it's been very good. I think they have managed to get really good speakers from India, all the leading speakers. I hope you have enjoyed the symposium webinar series. Very heartening to see that quite a bit of people still there, despite the lectures were quite long here, which this one is almost an hour-long lecture, and I must really congratulate all the speakers to have that kind of patience to deliver these long lectures as well. Coming back to one of the things Raj as well as Pujarini requested me to really, as part of the valedictory function, is it possible to share some ideas or share some information about RSC as a society, as well as about our membership and how does it help in promoting chemical sciences. And so I would like to give a quick short presentation, I think, especially for the students who are participating in there, how you can become a part of the community in India, and really how RSC can support you in promoting your research, or even in fact engaging and networking with your peers as well. Give me just a minute. I would like to share a quick presentation. Raj, it's okay if I do a 10-minute presentation for the students on talking about benefits and the...
It's fine. You can continue. So we have time. 10 minutes. Fine.
Yeah, it would be a quick, fast presentation from me on RSC. I think my colleague Ajit did give you a brief outline in the first day in terms of what RSC is all about, in terms of how we came about and how we are involved in chemical sciences in India. Just to really give once again, I think we are a not-for-profit organization. We are world's leading chemical sciences community. And one of our, as it mentions, we are not-for-profit organization. Whatever revenues surplus we generate from our activities, we replow into promoting chemical sciences across the world and even in India. And our vision is to be a leading voice and trusted partner for science and humanity. We have a host of activities we do. Most of us, most of the students know us as a international publisher. You would know about we organize conferences, but I think a lot of other things we also do. We are a global membership organization. We do, again, I mentioned to you, we are a science campaigning policy. Like I mentioned about, we did some reports on gender diversity, diversity and inclusion. Also, recently we have come about on digital futures. I think how digital is going to make an impact on chemical sciences. We as a society, we are looking at the newer trends and how chemical sciences is impacting us as well. And finally, we are also an education facilitator. We have a lot of resources which is available for students to, especially at the school level and to a certain extent at the college level as well. We have an international presence. I think we have offices all over the world. You can see literally across all the continents. Though we have not mentioned anything about Africa, we have an office in Africa which looks after capacity building activities in a lot of these sub-African countries like Kenya, Ethiopia, where we are doing especially analytical chemistry courses for the community there. Apart from that, we also have an office in South Africa, South America as well, and Brazil. So we have become a more truly international organization with our presence. And we also have members over from 100 countries. I think we are truly, we are a global community right now. Just to come back to India, we started our office almost around 10 years ago in Bangalore. Right now, we have a fully fledged office at this huge building at World Trade Center in Bangalore. We have over 600 members with over almost 200 plus are fellow of Royal Society of Chemistry. India is one of the largest submitting countries. Second largest number of papers were submitted last year, and almost fourth largest highest number of articles published. It's almost around 2,000 plus articles published in RSC journals in 2019. We are very, very grateful to the community, and we value their contribution to our publishing activity in India as well. They are represented through various, apart from published authors, there is a large chunk of reviewing committee, as well as a lot of senior scientists are also representing on our boards as of journals. Quickly coming back to, as I mentioned to you, we are a leading chemical sciences professional body as well. We have different categories of membership. We have categories at student membership, affiliate, associate member, and a fellow. You can become a member based on your experience, based on your what level category you are. So affiliate and student membership is for undergraduate students and master students. The advantages of becoming a member are multiple. You can be part of several of our interest groups. You can be part of ChemStalks, which I'm going to talk about. You can be part of our scientific lectures, networks, and social events. And these all you get, you can access these aspects being a member of Royal Society of Chemistry. As I mentioned, you will be part of the professional communities, and being part of this professional community, you can raise your profile. You can join communities which can shape the future of chemical sciences. There are a lot of professional interest groups, which I will mention to you later on. You can involve in a lot of outreach activities. There is a tremendous amount of activities we do. As I mentioned, the first slide we mentioned, we have 5 local sections in India, which are being managed by our members. And these members, we give them a significant grant to do outreach activities. And these activities include from kitchen chemistry, scientific lectures, as well as organizing some seminars and conferences within India as well. And more importantly, you can also attend a lot of events based on your interest going forward, which you get basic discounts when you're attending these conferences as well. We have around 9 divisions on analytical organic. Each division has their own charter in terms of doing activities where you can get some support. And apart from that, you can also be part of any of the specialized interest groups, again, based on your state area of study and interests. One of the interesting part also is if there is a large number of students in one of the universities, they can join the student chemical, they can form a student chemical society, which is called ChemSocs. And a group of students we provide them resources and as well as support them in running that student club. And we also fund small activities which are run by these by the ChemSocs or the clubs. The whole idea here is to empower students to be involved in outreach activities in terms of how they can, going forward, they can be helpful in terms of building their leadership skills, their collaborative team effort. These are some of the things which will be requiring when you go for higher studies in terms of you're going for a PhD as well as in your professional career. And these ChemSocs provide you a platform to build those soft skills when you're being a student as well. Most importantly, these ChemSocs also will help you connect with RSC members, universities, local universities, and local sections who are driving some of the larger events as well. And these events could be, these ChemSocs could be complementary to the local section activities, as well as activities which are being supported by RSC office in India, including ours based out of Bangalore as well. Apart from being there are other benefits as well. You will members do have access to Chemistry World, which is a popular chemistry magazine, which is very good, which can put chemistry in a very simplified process, simplified language. We can understand that. You will also have an access to our newsletter called RS Voice, and apart from some access to some of our journals as well. Apart from RSC resources, you will also be accessing virtual library, RSC virtual library, where you have access to a lot of books from other knowledge partners like Springer, Science Direct, and also to access to ChemSpider, which of a database about 71 million chemical structures as well. And finally, I would like to mention that as part of a member, RSC has, we provide some grants and funding to students as well as senior faculty members who are fellows and members of RSC at various levels. We give some grants up to £2,000 to members to organize their own scientific meetings. And this is the aim is to really develop networks and really foster research collaboration between next generation of scientists. We give grants for PhD students to travel and attend conferences in India as well as outside as well. But again, these are limited. But again, we are very generous with these grants in terms of PhD students going across the world. And finally, we do also have a research fund for a university or college to do some research on their own. We are not a funding body like a large funding body like UKRI in the UK or Department of Science and Technology. We do really have some small amount of grants which we provide to smaller universities, lesser known universities and college for their research as well. And finally, we have a flagship program called Researcher Mobility Grants for PhD students and early career researchers. We give up grants up to 7,500 for collaborating with UK scientists. These grants are announced every quarter, so it's a rolling kind of a thing. Every quarter you can apply. Every quarter we announce the winners or whoever has been successful. But again, as I mentioned, I think these need to be a really very strong applications as well. And I encourage people from India to apply for these grants. We really don't have many applications coming for these grants from India as well going forward. So I would really welcome people who are already members of RSC to really apply for these grants and other things. We would really encourage that as well. And the future members who want to become, I think these grants will be open to you as well. And one of the things I would like to also mention that I think there is no bar or something like that. You have to be a member for X number of years to access these grants. I think we don't believe in that aspect, I think to binding people to be part of a membership. As long as you are interested or something, you feel that there is this, you can become a member and apply for these grants. And that's one of the important things we would like to mention it. That's about it. I thought I'll just give a quick update of 10 minutes rather than giving on. And I would be happy to ask one or two queries about membership, if there are any. Yes, Pujarini.
There are a few questions.
Yes, I think we can just maybe allow a few minutes to the students to see if they want to unmute themselves and ask a few questions on this. It was nice to learn about all the initiatives RSC has been taking, and it was particularly informative to know about the student communities that RSC has been encouraging. And does anyone have a question? I could see someone. Okay. And also the access to RSC laboratories and the various research grants that are available. So on students' parts, I just have a small question for you. So, would you just give them an idea, like what just to put it very straightly? So, what they can do to just apply for some RSC membership, some RSC affiliation at this moment? Most of our students are postgraduate students pursuing chemistry.
Yeah, one of the things I would, there is a form, student membership form, which is on the RSC website. I can send it across to all the students. We can send an emailer to, it's an rsc.org. You will get able to get the membership form there. The other one, as I discussed with you earlier, I think one, maybe the university can take a role and be a point of contact, to collect all the names and other things, and we can pass it on to RSC office. We will be processing. It's much more easier to do it, and we can do that as well. Right now, the student membership is around, globally, it is around £20 per year. But in India, we are giving it at around £10 per year, which is approximately comes up to 800 to 900, depending on the value of the pound. That's how we look at it.
Okay, thank you, Mr. Rajesh, for that good update on your part. So we'll be looking to associate with you in future. We would like our students, of course, to get engaged with RSC in whatever capacity that may be possible for them. I'm sure it will be enlightening for our students as well, and it will help them to take their careers forward, and it should help the university as a whole. Okay, so thank you.
There are a couple of
Mr.
questions on chat.
Are there questions in the chat box?
Yeah, one, I would like to mention that there's a mention by Adrika Banerjee. Is there any lifetime membership?
Sorry, yeah, I can see that question. Yeah.
Lifetime membership. Again, I will. There's another query about link to apply for RSC, which we will send out an emailer to all the students and other people.
You have already mentioned that. Yeah.
And as I also clarified in terms of how to apply, you just need to be a member of RSC right now for certain grants, and you can just apply for the membership, and then you can apply for the grants.
So just one small question. So is it necessary to be collaborating with somebody in UK for a research grant on the part of a faculty?
So I think we need to for especially researcher mobility grants, you need to really have a collab in UK where you will be spending some time for some time in the UK. We need that aspect as well.
Okay, thank you, Mr. Rajesh. So it has been very nice having you with us as the co-organizers of this webinar. So we are very grateful that you have agreed to associate with us. It was in a very short notice, to be honest, but we are very glad that you have associated with us, because RSC is a very esteemed organization, and thank you for sharing all this information with us. I think we will move forward to the last part of our valedictory session, and I'll just pass over the stage to Dr. Nandi.
Thank you, Dr. Pujari. So we almost finished our program. The time is also in the knocking. It's 4:33. So on behalf of the organizing committee, in this validatory session, I would like to thank all the speakers from day 1 to day 3, Professor Devabroto Maiti, Professor Shati, Professor Dr. Guillaume Bhansai, Professor Jerome Wazar, Professor Maria Isabel, Professor Taposh Kumar Chakraborty, Professor Dilip Maiti, Professor Devashish Das, and also Professor Tapan Kumar Pai. And I would like to convey my sincere gratitude to our Honorable Vice Chancellor for her constant encouraging. We did this one. And also, I would like to thank the external affairs manager of the Royal Society of Chemistry, Mr. Rajesh Parishad, for your kind help and different technical issue. And also, last but not the least, I would like to thank our course coordinator, head of the Department of the Chemistry, Dr. Tanmoy Chattopadhyay, who could not attend this technical session and also validated due to some technical issue, but he's listening the lecture and all the program through the YouTube. Thank you, Dr. Chattopadhyay. And also, I would like to thank all the students for helping from different aspects to make this event successful. And with this brief speech, I would like to hand over the session to the Pujari to conclude this session. And also, in the end of the session, I am requesting all the participants, please turn on your webcam so that we can take some snapshot to keep this moment for our future memory. Thank you.
Participants, if you're listening, would you please kindly turn on your webcams? Thank you very much. Dr. Nandi, are we set for a snapshot?
Yes, I already took some pictures, so you can conclude, Pujari.
Okay. Thank you all for joining us. And well, there is nothing much left to say. So thank you all the speakers who have joined us for this webinar. Thank you to the Royal Society once again. Thank you to all the participants of this webinar. Special thank you to Professor Ashok Mollik, who has been with us listening to this webinar all this while. Thank you, sir, for giving us your time. And once again, I hope you have all enjoyed this webinar, and the Google feedback forms have been emailed to you, I think, in your emails, and it's also, the link is also up here on the chat box, so you can just click on that and submit the Google forms. I think you have until midnight to complete those forms and hand them over. So once you're through with that, you will be receiving your e-certificates in say a matter of 7 days at most. So thank you all for joining us, and have a good day. Thank you.
Thank you.
So bye, Guillaume and Dr. Maiti. So thank you, Professor Mollik, for being with us. So
thank you, Raj.
Okay, Guillaume,
yes,
you are muted.
Sir, you are muted.
Oh,
Professor Mollik, you are muted.
Professor Mollik is muted.
Yes, I always enjoy the lecture of Professor Maiti, and
thank you, sir.
Professor Maiti is a product of Belur Ramakrishna Mission, where I was a student and I was a teacher. I was a teacher.
Wonderful.
And I see in your group our student from Jadavpur Oisani Sur. She has joined possibly.
Yes, sir. He did well. He did very well. She did very well, and now she is in US. I just heard from her, supervisor recently that she's doing excellent over there. So thank you for, sending her to IIT Bombay and giving us the opportunity to, to train her a bit. So she's doing quite well. Thank you, sir.
Her father was also my student at Vidyamandir in the higher secondary and in the BSc level. And then I left Vidyamandir and I joined Adapur in 1984. Okay,
great,
thank you. Expect